practical session on IAR embedded system workbench. So starting with MSP 430, let's start with the numbering convention. For any microcontroller, it's very important that what are the peripherals attached to it, what are the parts incorporated in it, and what are the parts we can interface to it. So for that, the features are very important. How much memory we have, how much data memory we have, how much program memory we have, and that we can all know with the help of just by knowing the number convention. So let's start with this. This is a typical MSP 430 number convention which has MT, FA, FB and MC. Here MT refers to the type of memory we are using. If it's a RAM, if it's a ROM, then it's C. If it's flash memory, then it's F. If it's OTP, then P. Or if it's EEPROM, then it will be E. Similarly, for FA and FB, this FA generally represents the generation of MSP 430 on which we are working. Here, as you all can see, these are the first generation microcontrollers, MSP 430 microcontrollers. These are the third generation microcontrollers. These are the fourth generation microcontrollers. And on the basis of combination of FA and FB, we can tell some of the basic features of the microcontroller which it has. As for example, if it's MSP 430, say F, flash memory, it's 10, then it means that it is a basic microcontroller of first generation. Let's say if the number is MSP 430 F31, then it means it has a facility of LCD controller and we can directly interface a LCD controller with the help of programming. We will not require any other external hardware for the connections. In the similar fashion, if it's 4.4, we have LCD controller as well as hardware UART and hardware multiplier. This hardware multiplier is a sort of accelerator which helps to speed up the process of the microcontroller, because it's very important for us for an efficient application of embedded system to work properly, that how fast it works. And it depends if we have an extra facility on the microcontroller board such as hardware multiplier, we can easily multiply out without putting the load on the ALU, and it will require a very less number of T states or frequency cycles through which we can implement the application. Similarly, the last M refers to the type of memory. If it's 0, then it means 1 KB of ROM and 128 byte of RAM. In the similar fashion, if it's 9, then it means 60 KB ROM and 2 KB of RAM. Fine. So with the help of this particular naming convention, which is generally valid till 4th of generation, and moving on to 5th generation, you have to refer the data sheet for the numbering convention, because the number of points have increased a lot in that. So I have just considered till 4th generation over here. So can you please tell me what is the general feature of MSP 430 F435? F refers to flash memory. 43, fourth generation microcontroller. So everyone has the sheet. The above part is the naming convention, numbering convention, and the lower part includes the instructions which are there in this particular microcontroller. So on the basis of this, can you tell me MSP 430 F435? What are the basic features? The basic features are, it has a flash memory, then it has a LCD controller, hardware UART, 16 KB ROM. Fine. And 512 bytes of RAM. Issues? Clear? Okay. Now let's move on. Can you please tell me which type of architecture is this? Which type of architecture is this? It has a separate two types of memory, 16 KB code memory, 512 bytes of RAM memory. think about it. I will come back to this point. Let's first move to this particular thing. This is where I have started. This is the kit which we will be using in the lab session. MSP430F5529LP. As I have told you, till the 4th generation the numbering convention is very simple, but as you move on to the 5th generation, there the specific you have to look after each data sheet. Okay. So here it's the 5th generation control. The specific point which I want to tell you is last one, LP. LP refers to low power. It's a low power microcontroller. That means in all the applications where the power is constrained, we can use this particular kit. Now why this ultra low power is important? It is important because almost $50 billion spent every year on batteries. 2.9 billion used batteries are thrown away each year in US only. 50 billion additional connected devices. As you all know that we are on the peak of Moore's law, where the number of devices has increased a lot, and in the coming generation we will be moving towards the 3rd generation on the 3rd degree, rather 3rd dimensional Moore's law application. So the number of additional components will be increased a lot, and which requires some more power, as well as the distributed sensor network application, where the sensors are distributed in various areas, and we require a separate power supply for each sensor network. So their power is a very big constraint, and if we start working on the same microcontroller which requires lots of power, then it will be very difficult for us to sustain in the coming world, because batteries means a carbon outtake which will at last inform us, hurt us at last. So this power factor is very important, and now here the MSP430 plays a vital role. It plays a vital role because it works in 2 modes. First one is low power peripheral mode and DCO mode. Now this DCO is demand CPU clock. So whenever the microcontroller is not in use, at that time it will just require 0.4 microampere of power of current. When it will be used, it will require about 170 microampere of power. So by using this type of parameters, the application will require very less amount of power. Say for example, an application such as we have developed an embedded system for a industry-based application. Say we are monitoring the various sensors through virtual instrumentation panel, and these sensors are telling us whether the temperature is above the particular cutoff or not. If the device gets heated, then in return the embedded system should ideally cut that particular machine or device. So this application we have to design, and if we use MSP430 for this particular purpose, then until the time that interrupt has received, interrupt from the sensor which will tell you that the temperature has gone over the limit, till that point we receive that particular interrupt, your system or your microcontroller will be in a low power peripheral state, because of which the amount of power required will be very less. Once the interrupt has encountered, your microcontroller will again become active, and at that time it will ask for on-demand CPU clock and will start working in this particular mode. Now here you can see the amount of frequency is increased. Amount of frequency increase, that means more power will be required. And here the amount of power required will be less. So all such type of applications where we have the constraint of power, MSP430 can be one of the best example of using such microcontroller. Now here are some of the applications, particularly when we receive interrupt. The interrupt can be received by a timer. Say for example, we are counting number of faculties coming to this particular classroom from the gate, and we have employed some embedded system that will count individual. It can be, we can use the 2 laser sensors, 2 lasers. The moment it will cut, it can tell you, or some optocoupler device, or something else, maybe ultrasonic sensor or an IR sensor in the simplest case. So whenever a person came, let's say we have a capacity of 60 seats. So our microcontroller will be in low power mode till the count reaches 60. That means we have to check on the basis of timer. If interrupt occurs and we reach on the stage of 60, we can ask for on-demand clock and cut off our power supply till that point. So from such type of application, we can reduce the power consumed. In the similar fashion, we can use ADC or DMA. DMA, as you all know, it's a direct memory access. Whenever we want to transfer between the 2 peripheral devices without the interference of the microcontroller, what we do is First we send a request from peripheral device to a microcontroller that we want to use your system bus, that address bus, data bus and control bus. For our requirement, it can be data transfer or any other thing to connect to that particular processor. And once the microcontroller allows you or acknowledge you the signal, then after that you will directly transfer the data from this peripheral to the other peripheral. Now between this transfer, once the data lines or address lines has been allocated to the peripheral, the requirement of microcontroller reduces. That means we can program it in the low power mode. And once it's come back, after the completion of the data transfer, when a request back condition is received from the second peripheral or the data transfer is done, then at that time we can come into the on-demand clock. Fine. So all such type of applications can be programmed in the low power mode. Serial communication, RTC, real-time clock wherever required, or through an external interrupts also. Okay. So this was my question earlier. What is the type of architecture over here? It's von Neumann or Howard? Which type of architecture? From seeing this, anyone can say that's a Howard architecture, where the program memory and data memory is different. But to be specific, it's not a Howard architecture, it's a von Neumann architecture in which the memory is present on a same memory device or memory chip. So here is a memory map of a MSP430 microcontroller, where you can see we can interface in a fifth generation microcontrollers, we can interface near about 1 MB of memory. And in this memory, you can say it's all are inbuilt over here. That program memory is in this block, data memory over here. That's a von Neumann architecture, not a Howard-based architecture. Any doubt? Okay. Now, depending on the which particular microcontroller we are using, the size of the partitions can vary. As in this particular case, we have 128K of flash memory, and this 80 locations are given to the vectors, interrupt vectors. Then we have some RAM memory, USB memory space for bootloader, and other things. Now, here is a comparison between the two fifth generation microcontrollers. So it's very difficult for you if you try to learn these particular things. It's better to look at the data sheet and start working from there only. The resistors will change in each and every microcontroller. If it's 5529, the resistors will be different. If it's 5969, the resistors will be different. So it's better to look at the data sheet before starting developing the particular application. So here you can see the memory division between the various platforms are different over here. And similarly for the others also. Okay, so it's based on the von Neumann architecture where we have a same memory, and on the same memory we divide the particular things. And one thing, in this few of the higher generation, the 6th generation one, it has a facility of FRAM. Now this FRAM gives us the flexibility. FRAM gives us the flexibility to divide the partition the program or data memory. According to our need, we can divide the program memory or data memory. Say we require 5 KB of program memory and 20 KB of data memory, then we can divide it as per our requirements by using FRAM. Fine. And this particular facility is not available in the earlier parts of microcontroller, which requires a different interface every time for each memory. Say for example, 4 KB we require, we will interface a 4 KB flash. Then let's say 8 KB we require for the particular other different thing, program memory or data memory, then we will interface that. But if we have FRAM, then in that we can partition it with the help of program, whatever memory requirement we have. During the initialization stage of any program, we can define how much program memory we want and how much data memory we want. Okay, having such a basic idea of these particular things, let's try to design a particular microcontroller application in which say a sensor is there and we are trying to drive particular applications with the help of MSP430 microcontroller, so that we can have an idea of how we interface particular hardware with the microcontroller. So let's say that we are using Okay, so let's say we want to interface some motors and other devices with the microcontroller. So here is an example of interfacing of MSP 430G256. It's a second generation microcontroller, and in this particular microcontroller we have connected some switch. It will switch on the device. When the device will start working, it will take the input from a sensor. It can be any sensor. It can be a CNG gas sensor, or a fire sensor, or a temperature sensor, any sensor you can use. So here we take some input from this particular sensor, and after taking this input, if our temperature is above certain limit, then the buzzer will be started, or we can switch off a particular device which is connected to a relay. So here it's a application of how we can use this particular microcontroller. In any of the microcontrollers, there are certain ports which can be programmed as an input or output. If we are using 5th generation microcontroller, then in that particular microcontroller we have almost 10 ports, port 0 to port 9, which can be connected in either an input or an output mode. For that we have to program a particular resistor. So for constructing any embedded system application, we require to design or program that particular ports. So in this particular application, as on the P1.5 this buzzer is connected. So this particular P1.5 pin, this connection mode will be output, isn't it? Okay, this buzzer will work as an output device. So we have to program it as an output pin. Similarly, when we press this particular switch, the device will be switched on. That means this will be working as an input mode. In a similar fashion, we have connected one red LED over here. If the device is active, then after every 30 seconds this device can blink. We can program it in that manner also. So this will be working as an output or input? Output. As output. Similarly, we are taking input from the device, which is connected with the help of ULN 2003 driving IC to the microcontroller. Here you can see port 1.0 is connected to particular device. Fine. If we are getting sense input from this particular device, that means this is working as an input. So we have to program 1.0 as an input, 1.5 as an output, 2.2 as an input, 2.3 as an output, and the other devices is connected through ULN 2003 to the relay, and so on. Fine. So in nutshell, what we have to do it by designing any of the embedded system application, we have to program the ports either as an input or output, or as an output. If we are able to do that, then any of the application can be designed. Fine. Now how to program these particular ports as an input or output? It depends on the resistors that particular application is having. So I will come back to this particular slide later when we will be talking about more on the ports, how ports are interfaced to a microcontroller. Now, this type of application can be used in cars also. All those cars which has CNG or LPG, we can design our own embedded system application, and it will hardly cost us 1500. Okay, if we are using a development code, and just we have to program either as an input or as an output. Now let's come to this one. MSP 430 is a RISC processor. That means number of instructions will be very less. In total, we have near about 51 instructions in MSP 430 microcontroller, which can be used to program it. Moreover, it's an orthogonal architecture. Now this point is very important because it gives a lot of flexibility by designing any embedded system application. When it is said that any device is orthogonal architecture, that simply means while writing any of the instruction, you can use anything as a source or anything as a destination. You do not have to care about anything. As for example, in 8085 we have a restriction that we cannot directly transfer to a memory. There is a restriction there. Or in 8051 also, we have a restriction we cannot directly transfer to a memory. Also you remember? But in this particular case, we can directly transfer from one memory to other memory. Also, or between from one memory to a register, or from register to a memory, or any immediate data to a memory. So it's an orthogonal architecture that we can do anything. All of the registers are available to us, even the program counter or stack pointer. We can give program counter any value even in between the program. That means a sort of a branching instruction we are doing. That means our program control will be shifted towards the new location which is given to the program counter now. So it's based on the orthogonal architecture, that is, we can use any combinations of the available registers, memory and the program counter or stack pointer available. There are total 51 assembly instructions, out of which almost 27 are the core instructions and 24 are the emulated instructions. Now this term emulated instructions means that it will depend on the core instruction only. If you give an emulated instruction to assembler, it will not give you any opcode. The opcode will only be given to only the core instructions. For all the other instructions, it will convert it into a core instruction, then that opcode is used of that particular core instruction. That is an emulated instruction. So for beginners, it's better if we can learn this 27 instructions, we will be in the commanding mode of doing the programming stuff. But we can also use these emulated instructions, these 24 instructions which do not have an operational code but uses the core instructions for their programming. MSP 430 instructions are divided into these 4 parts: data transfer, arithmetic, logical and program control instructions. Now here is some of the instructions. These are the single bits or single operand instructions. Sorry, double operand instructions. Move dot B. This B refers to bit. Okay, so we can work on either a byte or a word or extended word also. That means out of 20, we can work on 16, 8 as well as on 20. So this dot B is used for if you are working on 8. So move dot B source to destination, that means the content of source is moved to the destination. Any of the combination can be used. It can be R0, R1, R2, R3. Add dot B, that is used to add the two, source plus destination, result will be stored in destination. Add C, that is for the carry flag. You all have the list of instructions present in this particular microcontroller. Subtract B is subtraction. It uses a complement for subtraction. That means we have to do destination plus complement of source plus 1, 2's complement method of subtraction. Then subtract with borrow, compare the two numbers, and depending on these two numbers, whether the source is greater or destination is greater, your flags will be set. The major flags which we will be using will be carry flag, zero flag, and overflow flag. Okay. We do not have any parity flag like in 8085. It has a carry flag, overflow flag, and zero flag and sign flag. Now this DAD instruction, it's the same as in 8085 or in 8086, which is used for decimal adjust. Okay, so whatever you are doing, our source plus destination, add these two, then a carry flag, and whatever the result you will get, that will be adjusted into the decimal BCD number. Then bit instruction, this is used to find source and destination. Now what is the use of this? Based on this bit instruction, you can check what is the status of each bit. Say for example, we have written bit. Anyone has marker? Let's say we have written bit dot B hash 00001 and comma destination will be any register. So what it will do, it will add the source from the destination, and depending on the output, whatever bit we are checking, depending on that we can program any of the conditional instruction as JZ or JNZ. Any of these instructions can be used. Okay, this I will tell you. Let's move on XOR. XOR is a simple one. It is used for finding XOR. And the last one is AND instruction, which is used for finding simple AND operation, and the result will be stored in the destination. These are the other instructions. These are single operand instructions. These were two operand instructions. In single operand instructions, we can rotate the value in the destination. In 8085 and 86, we are restricted with only rotation on the accumulator, but here we can, since it's an orthogonal architecture, we can rotate any of the registers. With RRC, carry flag is included by rotation. In RRA, carry flag will not be involved in rotation, but it will be updated depending on the value of LSB. Okay, and this MSB will be repeated. Whatever value we have, this will be repeated. Similarly, push instruction, which is used to push the content onto the stack. And when we push the content onto the stack, then the corresponding stack pointer will be reduced, the top of the stack will be reduced, and the value will be uploaded on the stack. As say for example in case of the jump instruction or say conditional call instruction, whenever we call at particular location, the current program counter is uploaded on the stack pointer. So wherever we return back onto the main program, that we can take from the stack pointer and start executing our program. Or whenever in case of any interrupt occurs, then also we have to jump on that particular location and save the current program counter value onto the stack.
There is no pop operation.
There will be pop operation. Push operation and pop operation, both will be. Then call instruction to call the rotate, return, interrupt. These are the few of the instructions which are one operand instructions. Now here are the jump instructions which we can use. Jump to label if 0 bit is set. Jump to label if 0 bit is reset. Depending on the condition, we can do it. All based on the flag registers basically. Jump on carry, jump on not carry. Then jump to label if n XOR v result is 0, then we have to jump. This v refers to the overflow flag. JL refers to jump to label if n XOR v is equal to 1 and so on. So these are the basic instructions which we will use while programming the microcontroller. Now these are the emulated instructions which I told earlier. That emulated instructions don't have their own opcode, but they use the opcode of the core instructions. So till the time what we are saying were all core instructions, these are the emulated instructions. As for example this one, ADC.B it will add carry to the destination, but actually the instruction which will be performed will be this one. ADC add C.B #0, DST. That means in the assembler it will be adding 0 to the destination and a carry. Remember this instruction add C. So Z source plus destination plus carry. In actually this will be performing, but it will be emulated as this particular thing. Similarly, BRDST, this is a branching instruction. We can go to particular location and we can use move DST program counter. Remember it's an orthogonal architecture, that means we can use any of the combination. So move destination PC. Okay, move destination program counter, that means whatever the value of destination is, that will be into the program counter, and it is a branching instruction. That will instead of following a particular tree, we can move to some other branch and run a particular code program. Then these are few of the instructions which all come into the emulator. If you have any of the doubt, you can ask it. It's a very simple and straightforward instructions. CLRC, clear carry bit, clear negative bit, clear 0 bit. Dat C, add carry to the ticket. Dat C, that is emulated from dat instructions, DADD. Dat instructions, that is decimal adjust to the register. Dat B, that is 0 plus DST, and after that the result will be decimally adjusted. In a similar fashion, these are the instructions, increment instructions, then disable interrupt, enable interrupt, or increment instructions. These are the basic instruction assembly language instructions which we can use. Actually, it will be converted into a core instruction, and then the opcode of that core instruction will be inserted into a device. All the hex code will be of the that particular core instructions. Okay, sir. Emulated is sometimes simple to use. As for example, here this negative bit. This is easy for us to use. It's assembly language code, English type code, very easy to use. But if someone like this BIC #4 is it's sometimes confusing. So it's very simple for us. If you are programmed, if you have done through the programming, then it will be simple for you to use this emulated instructions because it is a direct application of that core instruction.
Total number of general purpose register.
Total number of general purpose register again depend on the type of the microcontroller uses. If it's a 5th generation, then here about we have 12 registers. R0, R11. Total size is 1 MB. So 16 bit to 20 bit, depending on the microcontroller again. We can have 20 bit also in the extended case, but we can use it in the 16 bit or 8 bit also. So I am showing you just the data sheet of this particular application. Again, for everything you have to refer the data sheet. For designing any of the application, see, this particular microcontroller data sheet is only of 1000 pages. Only 1000 pages. So it will not be possible to cover each and everything. The best thing is, you design an application, then start thinking what are the basic parts which we require. And then take that particular look in the data sheet and start working on it. Any of the application. Suppose you want to design it for anything, let's say our input are analog in nature. We want to convert it into digital format. So initially, just look at ADC converter, whether it's inbuilt in your microcontroller or not, depending on the microcontroller uses. As for example, in 8051, we don't have ADC converter. We have to use a separate circuit. But if you are using a PIC microcontroller, it has the inbuilt ADC. Similarly, this device has an inbuilt ADC. So depending on whether you have the ADC or not, and depending on your application, you have to take the look on that particular thing. Because everything will have a resistor, and that you need to program for working it properly. I will come on to that later. Let me show you first the instructions over here. These are the double operand instructions, and these particular thing tells us that in this move.b instruction, which of the flag will be affected? Overflow flag, negative flag, zero flag, carry flag. Which flag will be affected? For that, can we use any jump instructions or not? These are the jump instructions format, and depending on format of the condition, the instruction is like this. It has a opcode, then whatever condition it's on working, and 10-bit sign PC offset, whatever offset you are using. Okay. And then these are the emulated instructions which we have already discussed. Okay, so till this time I haven't talked about the number of clock cycles required in any instruction, because again it depends on the microcontroller. As in this 5th generation microcontroller, if you are using interrupt, then it requires a near about of 5 clock cycles. Okay, might be if you are using 2nd generation computer, it requires 8 clock cycles. So again it depends, and we cannot learn these particular things. For that you have to refer to data sheet. So if you are designing a program for delay, for that you have to look at the data sheet, how much clock cycles we need for programming it for delay. Generally, if you are using register to register transfer, it will be done in 1 clock cycle in most of the cases. But for all the others, if you require some sort of peripheral and other, then it will require near about 3 to 4 clock cycles. So for that, you have to refer the data sheet and how much clock cycles it will be needed with that. Now let's come on to the addressing mode, because it is very important to learn this addressing mode, since we have to after all address the memory every time. So for that we require addressing mode particular, and this particular application microcontroller has a 7 addressing modes. That's the register addressing mode, whenever you transfer from one register to other register. Then index addressing mode, it is required for calculating the addresses. Index value is used as address. Say for example, here it is written move.w to R5, 6 R6. That means whatever the content of R5 is, add this index value. So in such type of applications, instructions, always an index value will be given. It can be of 8-bit or a 16-bit or a 20-bit. So you have to add this value to R5 register, then 6 to this R6 register, and whatever content we are having, this will work as a source, this will work as a destination, and this value from source will be transferred to the destination location. Fine. So this is index addressing mode in which the indexes are present. Let's look at some of the first register mode instructions. In the register mode, we will transfer from one register to other register. It can be of 8-bit, 16-bit or 20-bit. Then if we are doing for 8-bit, in that case, we will be using from 0 to 7. The lower byte we will be using if it's 8-bit instruction. Say for example, move.b R5, R4. That means .b refers to byte. We will be transferring from R5 to R4, from source to destination, and the amount of data will be transferred as 8 bits. So in that case, we will be required only from 0 to 7, and 8 to 19 will be clear. This will be 0. Fine. Similarly, it can be used on word, which is of 16-bit. In this particular case, if let's say the register size is 20-bit, then in that case, value will be from 0 to 15, word 16-bit, and from 16 to 19 it will be clear. That means its value will be 0. And same is for address word operation. This address word operations is generally represented with a A suffix. That means if we write this BIS A, that means we are using 20 bits. Fine. So instruction format will be save, just it will be BIS A. Or if you want to use 20 bit move instruction, then move A. Move A R5, R6, source, destination. Then it will be used for a 20 bit. Say this is the example. Let's say this BIS, which is this is used for bit set. Remember this bit set. BIC for bit clear. So depending on the value of R5, the value will be set in R6. Let me tell you. Let's say we are using R5 is equal to say 1. Let's say RS is equal to R5 is equal to this one, and let's say R6 is equal to. So if you have written BIS.B, that means we are working on byte. And let's say we have written R5, R6. Remember, this will be source, destination. So depending on the source, your value will be set in the destination. Fine. Or in other words, you have to perform R5 or R6 operation. Depending on the value of R5, the which value set over here. This is value number 7th position. Then at the first position, these values are set. Then that means these only values will be set in this R6. The other values will be remain set. This will be 100% set. Fine. Similarly, if you are using BIC instructions, BIC.B, let's say R5, R6. This refers to bit clear. And which bit to be clear? Depending on the value of R5, you have to clear the value in R6. So depending on R5, that means this value first and second will be clear. So in action, you have to do R5 and R6 operation. So the result will be R5 and R6. This result will be 1, 0, 0, 0, 0, 1, 0. Fine. This can be used for any port also. As we know that after all we have to program each port as an input or output. Okay, so for that we have different resistors. As for example, in case of this microcontroller, we have PX DIR resistor. That's a port direction. In which direction you want your ports to be working. If it's 1, then that means that particular port pin is working as an output, and if it's 0, then that means that particular port bit is working as an input. So let's say we want this particular port has 8 pins from 0 to 7, and we want pin number 5 to work as output, and let's say other pins to work as input. So what code we have to write? We will write move, either move, or we can use also this BIS move. Which one we want? Pin number 5. That means move dot B, then source to destination. So the source will be 0 0 1. Okay, that means this fifth one, comma, whatever number you are using, PX DI. Now, by using this particular instructions, what we have done is we have programmed pin number 0, 1, 2, 3, 4 as an input pin number 5 as an output pin number 6 as an input, and pin number 7 as an input. So for doing any programming, you have to after all set these particular ports. So for that we can use resistor addressing code, in which we can use either put this content in some resistor and can program it. Okay. In the similar fashion, this is for the programming, that giving the direction of particular code, or let's say we want to take some bit from as an input. Then for that we have resistors such as PX in. So we want to take the value which has k on this PX in resistor to any of our resistor. The simple command will be move PX in comma, let's say R6. So this whatever input value is coming on this particular port, that will be in the R6 resistor. We can do it for bit also. Move dot, this is B. Fine. In the similar fashion, if we want to send something at the output port, the command, the resistor which is generally uses PX out. So let's say we have written move the value in R6 at PX out. So let's say we have connected some LEDs on particular port, maybe P2 out. On the second port we have connected some LEDs, and we want these LEDs to blink, let's say. So for blinking these LEDs, every time we have to give first 1, then after a delay we have to give 0. That means move in R6 we will have FF to this particular port, all these LEDs will start glowing. Then with a delay, after a delay, we will give move 0 0 comma P2 out. So it will start at off. It will switch off condition. Okay, so these can be used for any of the input output port also. Okay. This I have told you, if we want to use this for 20-bit, we have to use dot A. For 8-bit, we use dot B. For 16-bit, dot W. For 20-bit, dot A. As in this condition, this X dot A R5 comma R6. Let's say the value of R5 is AA550 and R6 is 1111. Okay, so BIS operation, that means OR operation. All operation will be performed and result will be updated in R6. The source will be same. Index mode can be on, it can work on 4 types basically. You have 1 MB of memory, and this 1 MB of memory can be divided into 2 parts of 64 KB each. This one. 1 MB memory, that means 00002. This is a physical index, and it can be divided into 64 KB each. So you can use index mode on this 64 KB or on this particular 64 KB or as a whole. Okay, so the index mode can be used MSP 430 instruction with index mode in lower 64 KB or it can be used in higher 60 above the lower 64 KB or overall, or MSP 430X addresses instruction with index mode. Fine. The main thing is that you can program index in index mode by using this part or a whole. Okay. So here is an example of how it is done. Some CPU register is there, and in index mode always our index is given. This is the example of indexing. See, 1000 R5, comma 0F000H R6. Fine. In this particular case, for finding the effective R5, you have to add this particular index. So all the instructions which come in the index mode, in that case you will be given one index. So here we are finding R5 plus 1000H. Okay. And similarly 0F00 plus R6. Whatever the values, let's say the value is this one. So this is for R5, and similarly we can find R6 plus F000, and then the result will be added and it will be stored in the destination. So here it is. First register will be given, then some index will be given, these two will be added, sign addition will be done, and finally it will represent some memory address. From that particular thing you will transfer one of the data to the other. If it's add, then it will find this for the source as well as for the destination, then add source from a destination, that means source plus destination, result will be stored in the destination, but through indexing. Yes.
Destination address will be 0078 at the end. After addition.
Destination address will be
After addition.
00778H. Yes. No, this is see, with the help of R5 plus 1000, this is used for source. The content of source is present on this particular physical address location. Physical address location will be of 20 bits. So we can take source from this particular location. For destination, we will use this plus this. This is the location of destination. Then after this source plus destination, and the result will be stored on this destination location. This is the pictorial representation of this particular thing. See, this one is R5, and this is your R6. So R5 plus that 1000, okay, and it's in R6 plus F1000, and finally your result will be stored at that particular location, whatever the location is coming. Okay, so next one is the, okay, here I have only shown you the 64 KB version, but you can program it in other modes also. After 15 minutes, the IAR and also IAR will match. So it's very
इसमें नीचे रजिस्टर पे क्लिक करिए, नेक्स्ट करिए, रजिस्टर पे क्लिक करिए। वैल्यूएशन लाइसेंस टाइप कोड साइज लिमिटेड टाइम लिमिटेड बढ़ा ली फर्स्ट में लिए ओपन करके बता आपने मेल आईडी डाल दिया था उसमें भी मेल से नहीं पहुंची होगी एक मेल फॉर्म रजिस्ट्रेशन मेल होगी ना नहीं पहले आप उस पे जाइए डेस्कटॉप पर आइए स्केप करना दोबारा लगा के डालना इसी में देखिए
करेंगे तो एक लिंक आएगा, उस लिंक के थ्रू की आएगी, इसमें आपकी पेस्ट कर दीजिएगा।
काम कर देंगे।
लिंक को क्लिक करें, enter the license number to the license and click the next button. Thank you, and you have been assigned the following license number. Enter the license number into the license card and click the next button.
जो कॉपी करो,
कॉपी कर लिया?
की कॉपी करके पूरा पेस्ट कर दे, बस लाइसेंस मैनेजर में की को लाइसेंस मैनेजर में पेस्ट करिएगा।
सॉफ्टवेयर यही का सॉफ्टवेयर, इसी से हम लोग सारा काम ये लाइसेंस की कितने दिनों के लिए है?
फॉर 30 days।
30 days। का बता तो रहा है
कौन सा ये
Okay, before going on to programming with IAR, let's see the basic architecture of the MSP 430 so that we can move on with the programming part. MSP 430 architecture is a three-stage instruction pipeline. What are the three stages of instruction fetch or executing any instructions? Fetch, decode, and execute. That means it's a three-stage instruction pipeline. That means all these three steps will be done at a time in parallel. Okay. Initially it is fetch, then decode, and then execution part. So it will reduce your time period of execution. Then the second one is a 16-bit ALU. That means all the operations will be of 16-bit. If you want to perform AND operation, OR operation, or XOR operation, it will be done on 16-bit of data only. Then it has 4 dedicated use registers. These dedicated use registers are R0, R1, R2, and R3. This R0 is given to program counter. That means R0 will work as a program counter. R1 will work as a stack pointer. R2 will work as a status register, and R3 will work as a constant generator. Okay. What is the use of this constant generator? Whenever we require any constant value to be added or to be dealt with, then we use a constant generator to generate a constant value. Okay. Then we have a 12 working register or scratchpad registers. These registers are available to the programmer to program so that we can store the intermediate results. Then the CPU is connected to its memory through two 16-bit buses, one for addressing and another for data. All memory including RAM, ROM, this we have already discussed, that whole of the things are present on a single memory map. Fine. It's a C compiler friendly. That means you can also program in C language or assembly language. Embedded C you can use. Then it is a REST architecture which has 51 instructions, 7 addressing mode, constant generator to generate any constant value. Then single cycle register operation. This is very important. Whatever intermediate results are there, please store it on the register because it will require only one cycle to perform the operation. If you store it on the memory, then the memory fetch operation will require near about 4 cycles. Okay. Then we have one MB unified memory map. Then we also have extended addressing mode so that we can address 20 bit of data. ALU can perform AND or XOR, the same thing. Then the status register we have overflow, zero flag, negative and carry flag. On these we can use jump instructions to control the flow of program. Then hardware multiplier is present. By using this hardware multiplier, the multiplication becomes very simple and its number of clock cycles required for the multiplication is reduced a lot. Okay, so here are the registers of MSP 430 microcontroller. Then this R0, R1 program counter stack pointer, R2 and R3 as a constant generator and status register also. R3 is used as a constant generator as well as a status register. R4 to R15 are available for the user for programming. But remember, we can use any of the register including program counter. We can change the value of program counter through branch instructions also. Then we have an ALU which can be 16-bit or 20-bit depending on the MSP we are using. The one we are having is 16-bit, but you can also have other generation, 6th generation microcontrollers which is 20-bit. This is the content of status register. C for carry flag, Z for zero flag, negative flag, then interrupt enable for the mode, the low power mode in which the system clock is not required. In that case, you can use CPU off, oscillator off, so that the power will be reduced. So you can check the status by programming it to the By programming it, you can control this also and check its status on the status register, whether it's off or on state. Then we also have B, which is refers to a overflow flag. This one. Here are the details of each. These are all, B is the overflow flag. So whenever an overflow occurs from a 7-bit or MSB, there will be overflow will be generated. Then we have SCG1, this is system clock generator 1. And this bit may be used to enable or disable function in the clock system depending on the device family. For example, DCO, bias, enable or disable. Basically, DCO is, what is DCO? I told you. DCO is on-demand clock. So whenever we have to on-demand clock enable or disable, this can be done through this also. Then we have this FLL. This is the frequency log loop. FLL. We can enable or disable frequency log loop. That means we can divide the oscillator frequency by any amount. Suppose the frequency available is of 32 megahertz. We want to enter into the off mode, clock off mode. So in that case, we can divide it from 16 or from 32 so that the clock frequency will be reduced to 1 megahertz. For that, we can use frequency log loop, FLL. Okay, so from this, FLL can be enabled or disabled. Then this is for oscillator off, CPU off, interrupt enable condition, negative, 0 and carry flag. Constant generator, this I have already told you. We can generate a constant value such as 4, 8, 0, 1, 2, whatever required in the program. Okay, so we have 12 CPU register from R4 to R15 which contains 8-bit, 16-bit or 20-bit. For 8-bit we have to use .B extension, for 16-bit we have to use .W, and for 20-bit we have to use .A extension. This is how we handle the source register and destination register. In this case, let's say we are doing this, we are going to transfer data from a source to destination. Source register to destination memory. And let's say we are use a byte case. That means 0 to 7 will be used. These will be unused. Memory will be of 7 bits, 0 to 7. Let's say if you want to perform addition, the particular operation will be performed and the result will be stored in the memory. So this is how it works. If it's 16-bit, then 0 to 15 will be utilized register. 0 to 15 of memory, particular operation will be performed, result will be stored in the memory, or vice versa also. Okay, so these are unused over here, these 16 to 19. Okay, so this is the architecture of MSP 430 microcontroller. Here you can see lots of peripheral devices are here. We have inbuilt comparators to compare between the two values. We have ADC over here, we have DAC over here, then we have basic timer circuit. Timer can do two purposes. It can be used for compare. Okay, whenever we want to compare two values, that can be done through timers, or we can also count the values. It can also work as a counter. RTC refers to real-time clock. That means whenever we require, say, a particular day or a particular time, an embedded system to work for a particular time, then we have to use this real-time clock. Then we also have some hardware multiplier, 32-bit. CRC for all the electronics. What is this? Cyclic redundancy check. Okay, so here is you also have the option of checking your result with the help of CRC. Then we can also connect USB directly to our microcontroller, and in the development kit which we will be using an on-bit emulator also. Fine. Then we have some DRAM controllers, flash RAM, etc. The further detail can be seen in this particular slide. Depending on your microcontroller type, it can have 128 KB or 96 or 64 or 32 KB of memory, flash and RAM also. Then it has various ports, PA, PB, PC and PD. Remember, we have the ports generally which we will be using. It has ports from P1 to P8. Okay, and particular bit is referred as P1.x. That means P1.1, P1.2. Each port has 8 bits, 8 lines rather. And when these two are combined, this P1 and P2 can be combined to have 16 input output bits. It is known as PA. Okay. Similarly, P3 and P4 can be combined to have a PB. Similarly, P5, P6, PC, P7 and P8 as PD. Fine. Then we have some of the timers over here, timer A, timer A, timer A, timer B. These are the timers depending on you have to program the particular resistors. Then CRC and all these other modules. These are the general purpose input output ports. It can be independently programmed. That means each port line can work as an input or as an output, depending on whatever you are programming. These are the few resistors which will need to be programmed for having the port as an input or output. PX, DIR, it tells you the direction of whether particular port is working as an input or output. If it's 1, then it's for output direction. If it's 0, then it's input direction. Then this is input resistor. Whatever data is coming from the outside to microcontroller will come into this PX in. Through a port you have to input the data that will be stored in PX in resistor. Then we have PX out resistor. Whatever data we want to send to the external hardware or external transducer or external LCD device, that we have to send through this PX out. Okay. Then we have function select resistor. This is used to select, but whether we have to work as an input or output, or we have to select some other module. Here is a detailed diagram. Most of you have studied this yesterday. This diagram. It has PX out, PX input, PX DIR, PX select. This PX select is used to select between the module and between the input output pins which mode you want to work. That is done with the help of PX select resistors. This PX DIR, it will tell you the direction of buffer. That means whether you want to work as an output or input. According to that, this buffer will be configured out in this direction. It's a bidirectional buffer. It can be programmed with the help of this PX DIR. And you will take input through this PXIN. You can see this particular line. Okay, if its input is active, then this will work. If output is active, then data will be sent through this to outside. Okay, but you have to select it properly, PX selected. Whether you are using particular module or you are using the selection input output ports. That we have to do. Okay, this is interruptible input output pin logic. Non-interruptible, that means it cannot be interrupted. Whatever microcontroller we are using, MSP4305 5th generation, port number P0 and P1 can be interrupted, can be used as an interrupt, or it can be interrupted by any of the device. These two ports have the facility. The other ports do not have the facility of interrupt. Okay, so for all the non-interruptible input-output pin logic, the circuit diagram will be as shown. This we have already seen. This is some external hardware module which can be selected with the help of PX select line. And for the interruptible case, just one second, interruptible input output. One more thing is there, PNIES, PNIRQ. Fine. This is interrupt request. Okay, we have a hardware also, depending on the positive edge or negative edge, whatever you want to program, we can program it with the help of this particular resistor. Hardware multiplier, it has a multiply function. And basically two module performs its multiply function and multiply and accumulate function, which gives you 4 alternatives. This one, operand 1 unsigned multiply, you can perform unsigned multiply. Operand 1 as a signed multiply, operand 1 as unsigned multiply and accumulate, signed multiply and accumulate. You can see over here that this operand 1 will decide that what we want to do. Operand 2 will always be fixed, but this operand 1 will define whether you want to sign multiply or unsigned multiply. Okay, the result will be result high and result low. So how the higher bytes will go in this particular resistor, all the lower bytes will come in this resistor. Then we have other devices also comparator to compare between the two. So let's start with the programming part, and wherever we require this particular thing, we will refer to data sheet. Okay. So also IAR is stored in each row. It is in two systems. IAR is there. And Please return the hardware after use and do not mishandle the hardware.
ये बात सही है हमको
एक ही मिलेगा।
आप इधर
Other I guess we'll have to share. We have just 8 days. आप आगे हम आपको आपको मैं
हमारे बीच वाले सिस्टम में
in the state, see this is a development board. That means the basic interfaces are already done for you. Okay, as for example, you can see over here, this is a LED which is connected at port 1.0. All of those who are having this board, please check this one. P1.0 is a LED. It is already connected in this board. Fine. The P4.7 is also a LED. P4.7. Okay. P1.1 is a switch which is already connected. So these are the facilities which are already provided to us, which we can use in programming. We don't have to connect any hardware. P1.1 is a switch. Then these are the pins which are available to us for programming. Pin number 2.5, 2.4, 1.5, 1.4, 1.3. That means it can be programmed as an input and output. But for this we require some breadboards and other interfacing devices to be connected. Okay, capacitors, resistors, we require those. So we will use only these things which are available on this particular board for this particular session. Then it also has a FET emulator. You can see this. This is an emulator. Okay, this is directly available on your development board. We have one switch. This is for reset, and this is for bootstrap load. Fine. Okay. Shall we start with the programming? Let's move on to create a new project. Go on a project. Go on project. Then create new project. Project, then create new project. Let's say we are programming in assembly language. So go on this assembly, ASM. Then select this, expand this particular button. Then press ASM. Done. At this point. Okay. Fine. Define a location where you want to store your program and name this particular program. Let's say this is EXP2. Okay. EXP2 नाम दीजिए उसको.
By default PHP.
ना, this is by default EXP2. This is by default. ASM.S43. Okay. Whatever you name your project, that will be coming in your workspace window. Your workspace window has files such as exp1 debug, then asm.s43 and output. Completed.
Yes.
Project
एक बार में एक ही टिकट दिखा रहा है।
सर दोनों दिखा रहे हैं, चेक करिए। ये देखिए एक्सपेरिमेंट वाला अलग है, आपने एक एक्सपेरिमेंट टू अलग बनाया था। देखिए उसका अलग अलग है।
Okay, completed at this point. Now, remove this asm.s435. Close this. asm.s43. Close this file. Done? Close asm.s43. Completed? Done? Then remove it from this workspace window. Right click on asm.s43 and remove this file. Do you want to remove? Yes. Completed? Then file, new file. Okay. Now go on tools, then options, tool. In tool go on option. In option go on debugger. Just a second. Tool option and go on editor. Go on editor. Show right margin. In tab key function, select this insert tab. Insert tab. Insert with indent with spaces will be selected. Select insert tab. Okay. So we can use a tab window. Then on this right side, select show line number. Show line number. So that we can know that in which line error is coming. Fine. Done. Then click on OK. Then click on project, right click on your project and select option. Right click on your project and select option and select your device MSP430F149. Whatever device you are using, it's MSP430F5529. MSP430F5529. Right click on your project, then go on options, then select your device MSP4305529. MSP4305529. Completed? Done? Everyone?
जो उन्होंने पढ़ा था वही चीज
Go on this debugger. Debugger. Click on simulator. We have FET emulator on board, so we will select FET debuggers. Fine. Okay. Done. Completed till this point. Okay, now write your program. Now write your program in the editor window. So this is the program. We are using assembly language, but you can also program in embedded C. Fine. Hash include msp430.h. That means msp430 header file is included. Then after this, started the program from this particular location. Then stack pointer is initialized to 0280. But these are the directories predefined. We have to stop watchdog timer. What is the use of watchdog timer? Watchdog timer. What is the difference between timer and watchdog timer? It can restart after sunrise. Any of the application where we can use watchdog timer? In ATM machine, yes. Or anything. Let's say automatic card locker. Okay. When you swipe your card, if it matches with the password, it opens up. But after a certain time, if it doesn't open up, then watchdog timer automatically resets it. Okay. So in all such type of application, we can use watchdog timer. But here we don't want to use watchdog timer. That's why we have disabled particular thing. Stop this watchdog timer. Okay. Watchdog timer hold. Then after this, set up P1. That means we are using P1 port. Remember, P1.0 is a LED is connected on your development board on P1.0. Okay. So we are using bis.b #1, address of P1 dir. P1 dir is used for direction of P1 port. Fine. #1 means 1 in decimal. In binary that is 0000. Last bit is 1. That means 1.0. So this place will be set. BIS bit set. Okay, that means P1.0 is 1. That means this device will behave as an output. This port will work as an output. Isn't it? BIS means bit set. We use this command to set a particular bit. .b, that means we are dealing with 1 byte of data. #1 means this is decimal. We can also use 0001B. We can also write this one. Small b. This is, that is we are using binary. Okay. So this P1.0 is 1. Remember, bit set, source, destination. Bit set is used to set the destination according to the source. So here P1.0 is set. That means this P1 is working as an output. So we have connected LED on P1.0 port. Then after this, XOR.B #1 P1 out. What is this mean? P1 out is the output port. One is set. That means LED will be on condition, off condition. On condition. Then, okay, XOR will toggle every time. If it's 1, next time 1 gives 1 XOR 1 is 0. If it's 0, next time again XOR comes 0 XOR 0 is 0 XOR 0 is sorry 0 XOR 1 is next time when 1 comes, because we are using XOR B 1 comma this one. So when 1 XOR 1 it's 0, 1 XOR 0 it's 1. That means this LED will start blinking, but we have to introduce sufficient delay. That we have done using this particular command. Move hash, this is a decimal number, In R15 register, this data will be transferred source to destination in R15, then decrement R15. This R15 will be decrement from this one to 0. After this, we will check JNZ L1. Depending on this value R15, if it's 0 or not, this will go back to again this decrement. Fine. Once it's 0, you will go to jump to main. That means again to this one, and due to this, we will get a blinking LED. Isn't it? Any doubt in this program? We can use other things also. We can use BIS.B or BIC.B also. One will set the bit, one will reset the bit. That can also be used, or XOR can also be used. Fine. Then this is the last interrupt vectors. These are just defined ORG0FE DW reset because we are not using it. End of the program. Program shut time. Please type this so that we can proceed further. Any doubt till this point? Instructions are clear? These are, those are just the comments. Stop, pause, drop timer, P1.0 is output, and XOR for toggling. This is for providing the delay for reset interrupt vectors. These are the directories which are predefined. वेट का लेबल है, डिलीवर लेबल है कि हमें ये लेबल यूज करना हो तो वेट से कॉल करना है। ये सब इधर वाले जितने भी हम सबको लेबल की तरह यूज करते हैं। नीचे हमने लिखे DW रीसेट किए तो हमने उस लेबल को कॉल किया तो आप वो भी कर सकते हैं ताकि इसके बिना लेबल जहाँ जैसे वहाँ जेम से बात करने लेबल यूज करना जैसे हम पर्टिकुलर उस पर असेंबली पे जाओगे उस पर किसी भी जाओगे तो प्रोग्राम हो जाएगा। In fact, those who know how to work on Arduino, there is a platform named as Energia for this particular thing, MSP430. Those who have programmed on Arduino, you can directly program on Arduino or Energia as MSP430. It will hardly require to write each. Okay. Or one more software is there, CSS. That can support studio for MSP430. Completed? Okay, those who have completed, try this press the file. Please save this file by the extension .asm, as I have saved it from name flash led.asm. Then after that, add to your project. Go on project, click on right button, add this flash led.asm file. After this. वार्निंग है ना कोई बाकी हो गया Those who have written this program, please save this program with .asm extension. Then add from this experiment project name, add whatever your file name is /ready.asm. After adding this, please debug and download this one. Yes, download and debug. After adding it into your project, after adding the file in your project, as we do it in key compiler or MPI. In key compiler also we add this project. The same way we have to follow the error. Yes, sir. हाँ 10,000 15
रजिस्टर में ये लोड कर दिया अब ये
एक रजिस्टर में एक क्लॉक साइकिल तो 10,000 to 10,000 मैम 3 to 768 हर्ट्ज का इसमें कंट्रोलर आपका जो क्रिस्टल ऑसिलेटर तो वो बहुत जल्दी होगा
जंप भी हटा देंगे
जब हटा देंगे तो फिर रुक जाएगा Completed.
लगा देना कि कितने सेकंड बाद हो जाए कितने
Download and debug.
नहीं तो रात आने से ऐड हो जाएगा ये डिक्रीमेंट इसको इसके अंदर फिर यहाँ पे है फिर ये वो कुछ कैसे हो रहा है
इसको किया P1.0 किया P1.0 ये 4.7 ये आपने किसको प्रोग्राम किया इसको नहीं किया ये तो सिंपल बता रहा है कि आपका इम्यूलेटर के थ्रू प्रोग्राम आप इस पर फीड कर हाँ तो आपका प्रोग्राम ये है यदि P1.0 कुछ गड़बड़ है चेक करिए download and debug. So this is your debugging window. This one, these options over here. This is step over, step into, step out, next statement. So if you want to check step by step, you can follow this debugger. Let's say next one, stop WD. Let's do this one. So this is how it will work. This is the port 1.0 LED which I have connected. Okay. click on in color, click on this one. This. Done?
इधर आके देख लो भैया इधर जगह
And yes. Okay. Now, those who have done, please change the value of delay. Please increase this value of delay and check. Then again check. Place dot b hash 1. T1 दिया गया. Main text dot b hash 1 to address. सर मेन आपको
कितना नहीं यहाँ पे JNZ
हाँ N1 तो JNS नहीं होगा ना
यहाँ पे
साइन फ्लैग
अच्छा वहाँ पे
completed. Okay, in some of the cases there is a problem with stack. Stack pointer problem is there. Go on this tools, then options, go on tool, then option, then the stack, and recheck this stack pointer not valid at the program reaches. Okay, go on tool, you can also program in C language, but always it is said that assembly language is better than C language because we can have exact results in assembly one. You can also program combined assembly and C combined. You can use some of the instructions of assembly and then program it in C language. That we can also do.
हमने कराई नहीं
15 minutes before at 1:45. Okay. Feet अपने पास रख लीजिएगा, please. Feet up. And why microcontroller is so important? So the microcontrollers, the name actually came much later. Earlier it was digital controller or digital processor. It started in early 70s after the advancement of VLSI, which stands for very large scale integration. Earlier we used to have computers. Computer is not a very new thing in 70s or 1970s or 1980s. In fact, the concept of computer is much older. In 1940s, people were using computers, and the first computer was ENIAC. ENIAC stands for Electronic Numerical Integrated and Computer. Okay, and that time, in 1940s, when ENIAC was invented, they were using a vacuum tube because the transistor invention came much later in 1950s. Okay, so the BJT came much later. In 1940s, when the ENIAC was there, it used to occupy a large room like this. I mean, hardly having any significant amount of memory, maybe 1 kilobyte used to be a lot of memory at that time. And it was 1940s, and they used to consume a lot of power. Because for vacuum tubes, you have to excite the cathode by thermal emission, and that requires significant amount of power. Okay? Now it was, but the stored program computer concept was there. What meaning of stored program computer? The computer should be having a memory. Without memory, computers are useless. And in the memory, we have to have instructions, we have to have programs, and the computer will be operating on the programs, instruction after instruction after instruction. Before that, we used to have analog computers. Analog computers does not usually store programs. It's only realized by amplifier, op-amps, integrators, summer, differentiator, subtractor, and so on. Now, stored program computer requires a memory, and the memory is also realized by diodes, by vacuum tubes, 1940s. Now, in 1940s, that time, in US Navy, they had a challenge, Second World War, okay, 1942. That time, in the US, there was a requirement of the US Navy to calculate the range of a ballistic missile fired from a naval ship. It has been calculated and it has made the target very accurately. So this job was given to two universities. One was Princeton, other was Harvard in 1940s. At that time there was no VLSI, no transistor, nothing. People were realizing everything by means of trials. Now Princeton came up with an architecture, and the scientist behind Princeton was von Neumann. He was not originally, he was an immigrant, of course. He was a European who went to Princeton. He was a project engineer, and he gave rise to this idea of Princeton architecture, which is also known as von Neumann architecture. And Harvard also came up with an architecture known as Harvard architecture. So it was 1940s. Okay? So I would like to start with these two architectures. So what we have here is that we have a Princeton architecture. And we have Harvard architecture. So these are the two main architectures were given in that time. And what Princeton said, the scientist behind this was von Neumann, who was behind this. It is also known as von Neumann architecture. So what Princeton said, look, you have to realize a computer, and the computer has to calculate the range of the ballistic missile. So you have a computer, and the computer has a central processing unit. So you have a CPU, that's fine. Okay? So you have a central processing unit, CPU,
And what you have here, other than CPU, is a memory. That's all. And this memory is a single bank memory. So this is the memory. And whenever we have a memory, the CPU has to interact with the memory. So what it must say is the address. So there has to be the address box. Alright? And what the memory will give to CPU will be the data or instruction. So we say the data. And the data could be bidirectional. So it means the CPU can read from the memory or CPU can write to the memory. So this data flow is bidirectional. So this may be some number of bits that's not very important. So we say this is data or instruction. It could be data or instructions. Then of course, to coordinate this control, we have to have control signals. So this is the principal architecture. We say that we have single memory bank, we have a CPU, address, data, control. But Harvard said, no, we have to have a faster architecture. So what he says that there is a CPU, of course, the central processing unit. Alright, and then we have a memory here, and we have another memory here. So what he says that we will be dividing this memory into two different interfaces. And one memory is called the program memory. Program memory. And the other one is called data memory. So this is the idea of Harvard architecture. So for each memory, you have to have the address. You have to have the data. Now from the program memory, what flows out, this is the address which we keep from the CPU. What comes from the program memory is program instruction. Right? So this is instruction. And to the data memory, of course, there is a control here. Control signals are indispensable, they have to be there. And to the data memory, you have the data address. And then you have the data which is bidirectional. And of course, you have control. Now, when we say data, the data sometimes can be taught in various ways. Data can be available from various sources. You can give the data. Data can also be obtained from a sensor. So, for example, we would like to measure the temperature of this room. That's also a data. So, the data are sometimes mixed with IOs or input-outputs. So, these IOs are basically mapped in the data memory area. Just writing down for some time that part of the data memory could be the input-outputs. It means if there is an input connected here, that can also be data. And the data will be a part of the data memory. So IOs can be part of the data memory. Okay? Now when this architecture was presented to US Navy, that time there was no VLSI. The computer itself was very complicated. It used to occupy a lot of space, consume a lot of power in terms of hundreds of kilowatts. Now this architecture looks very complicated, right? Having two different memory, like a program memory and data memory, is complicated. You have to have independent address here, independent address here, independent interface for instruction and data. On the other hand, principal said, look, I don't distinguish between the program and the data. Part of the memory can be a program memory. This can be the program. And a part of this memory can be the data memory. Now that time it was difficult to build computers, and hence the Princeton architecture was adopted. So the Princeton got the contract it was 1940s when there was no VLSI. The computer building was an Herculean task. So in that time, Princeton architecture was approved and Harvard architecture was rejected because of the complexity. Okay? But after the VLSI came into existence in 1970s, there is increased use of Harvard architecture. The reason is this. Now, when you say Princeton architecture, the program and the data are actually placed in the same memory interface, same memory area. Now, program means instructions. When you say instructions, you have to read the instruction, then read the data. So, when you say instructions, instruction actually works on data. Program works on data. Say for example, if I say that we add two numbers, addition. Addition is an instruction. I say add. But when I say add, it is not complete unless I say add A comma B. Now when I say add A comma B or A comma let us say 50H or some values or say variable. So when I say add A comma some variable, in this case, this becomes a data. And the variable is located somewhere here. And this add A comma variable is an instruction located in the program unit. So it means if I have to execute the instruction, I have to read the instruction first. Now when the instruction is read, it goes to a register called instruction decoder inside the CPU. Okay, the instruction is decoded and the CPU understands okay this instruction is add A comma variable. Now it basically look for what is the variable. The variable is in the data memory area in the same memory bank. So this instruction will take 2 cycles. So it means read the instruction. Alright, and then just reading and understanding or decoding is not enough. You have to read the data. And then this instruction is followed by what is called read the data and execute. When it reads the data, it can process because CPU is very powerful. CPU works in billions of clock speeds. Okay, megahertz and gigahertz. So in that case, when we say read the instruction, it takes 1 cycle because you unfortunately have only one memory bank. You just have read first. First of all, you read the instruction. Then after you read the instruction, then read the data. And when you read the data, you have everything. You have instruction. Instruction is command. The command is that you have to add A comma variable, and the variable is also read here. Then execute. So it takes 2 machine cycles. For one machine cycle is read the instruction, other machine cycle is basically to read the data next. On the other hand, you see the Harvard architecture. Now, the same thing here that add A comma variable, I'll say add A comma variable here. And what is this variable? This is the program memory, and the program memory contains instruction. Variable is not here. Variable, the actual value of the variable is in the data memory. Right? Now you can also argue that okay, this has also variable here, so you cannot have access to the instruction and the variable at the same time. Okay? Because first of all, you have to understand what is instruction all about. The instruction is add A comma variable. And after you understand the instruction, then only you will be able to fetch the variable. Because variable must have an address. Okay? Variable is not available everywhere. Every data will have some address. And the address will be available in the part of instruction. So, what it does actually, read the instruction, And then when you read the instruction, you don't execute it. You execute subsequently. So for example, you ask your help that please go to my neighbor's house and get a letter for me, something like that. Now the help has to understand what is the instruction all about. It is to going to a friend's house and bring some material, right? And then he will understand the instruction, then he will go and he will bring the material. So this has to be executed in 2 steps. But you have the advantage of 2 different memory interfaces. So read the instruction and then read the data and execute the previous instruction. And when you read the instruction, you execute the previous instruction. Execute the previous instruction. Okay? Now when I say execute, I implicitly mean read data. Read data and execute the previous instruction. See, the instructions are always kept in sequence. Okay? Add a comma variable, multiply a comma c, something like that. So after the first instruction is executed, this is instruction number 1 and this is instruction number 2. So read the data and execute the previous instruction and read next instruction. So this is one cycle and this is the second cycle. So this is cycle 1 and this is cycle 2. Right? So when you say read instruction, you execute the previous instruction. Right? So the previous instruction must be read previously. If I have a cycle 0 here, this is again the previous instruction. Okay? Or I can tell that this is NS instruction, instruction N. This is instruction. Next is N plus 1. Alright? I say next. Next is N plus 1 instruction. If you say the instruction 1, instruction 2, instruction 3, instruction 4, instruction 5, I can always say that N is a number, a whole number starting from 0, positive number. So this is instruction N and the previous instruction is instruction N minus 1. So when I say read the previous instruction, it basically reads about the previous instruction here and then execute the previous instruction. Execute N minus 2th instruction. So this is cycle 0. So it means you read an instruction in the current cycle and execute in the next cycle. Execute the previous instruction means execute the N minus 1th instruction. Here you read the next instruction, execute the previous instruction means execute the nth instruction. So it means in every cycle, what you are trying to do, you are reading the present instruction and executing the previous instruction. Because once you read an instruction, you take time to understand what the instruction is all about. And you makes it clear that the instruction decoder. So when you read this instruction, the instruction decoder, CPU reads it. Okay? And then CPU takes some time to understand the instruction and the instruction can be executed in the next cycle. And in the present cycle, you execute the previous instruction which is already read. Now although when you say that this is our cycle we execute one instruction. In this case, for one instruction we spend 2 cycles. This is cycle 1 and this is cycle 2. So the principal architecture takes 2 cycles to execute an instruction, but Harvard architecture effectively takes, because every cycle has the 2 steps: read the instruction, execute the previous instruction, read the instruction, execute the previous instruction, and so on. So effectively, every cycle you execute one instruction. Effectively, right? Now I have a question here. Is there any instruction which is not executed efficiently in Harvard architecture? There are some instructions which will not be executed efficiently in Harvard architecture. We assume that instructions are little sequential. N minus 1, n plus 1, n plus 2, n plus 3, n plus 4, n plus 5, and so on. But do you think in a program always the instructions come sequential? It can be jump instruction. It means when you say that instruction 1 n, n plus 1, n plus 2, n plus 3, n plus 4, and so on, because automatically in cycle 2 the program counter will automatically increment by 1. Okay? How does it read the next instruction? It reads the instruction here n is address, right? So in this case it reads the next instruction which is n plus 1. So it automatically increments and blindly reads the next instruction and executes the previous instruction. So it assumes that the next instruction is available here. Alright? Because the present instruction cannot be executed in the same cycle. Because that the instruction to execute, you need the command and you need the data. And data is stored in somewhere else. Right? So when you read the instruction, you understand the instruction needs the data. There are some instructions which do not need any data. So for example, I have an instruction called NOP, no operation. It doesn't need any data. NOP means no operation, it doesn't need any data. Right? So, but there are some instructions which need data. Addition. Needs data. Even R A comma B, you say that R A comma B, this needs data. Now this data are also called operand. This could be that you R A comma B, R A and B, and store the content in A. Right? Now this A and B are implicit registers. Okay, if you talk about ATD5, okay, we have a instruction like NBR, A comma, maybe something like 25H. So it means this I stands for immediate data, which is available here part of the instruction. 25 is added to or is moved to A. It's a data transfer instruction. Similarly, you can also add ADI, add immediate, A comma 25, that's the addition instruction. So the data can be a part of the instruction as well. But the data has to be there, and this is the data are sometimes called operand. Operand and the data are the same thing. It means you operate on data. Operand means you operate on something. Okay, you operate on what? You operate on data. We say data processing. Data are meant to be processed, and the source of the data can be a human being, can be a sensor, can come from anywhere. It can be speech signal, you process the speech signal. It can be image processing, video signal. So the data can have many sources. So that's why we said that the facility that the data can also come from the external world. Now, leaving that aside, we assume that the instructions are stored one after the other, but that is not always the case. Sometimes you say that this is instruction 1 or instruction A. instruction n plus 1 and so on. Now when you say you have a jump instruction here, JB. Now the jump can go to anywhere, maybe next. So this next can be somewhere here. This need not be, the next instruction need not be at the next physical location. Now here is a departure. The instructions are not always stored physically one after the other. When you encounter a jump instruction, the instruction is somewhere else. Now when you encounter this instruction, the CPU in hierarchy architecture has no idea. It says read the present instruction, execute the previous instruction. Read present, execute the previous. Read present, execute the previous. Now when you say read present, execute the previous. Now when you say read present, you don't really understand what is the present instruction. You take some time to understand. Now it says this instruction is not a simple instruction. It says jump. It means it says that the next instruction is available not here, but here. Now when you read in the same cycle, we don't get the decoding information. The CPU does not give us the idea that it is jump instruction in the same cycle because it has to be decoded. So when you read this instruction, you don't immediately get the information that it's a jump instruction. Okay? When you go to the next cycle and you have already read the next instruction, it is wait. This instruction is not an ordinary instruction, it's a jump instruction. Which means the data is not available or the instruction is not available here. You have done a mistake. The instruction, the next instruction is available at here. This is the address of the instruction. Next address. The CPU, by mistake, has gone in this cycle after cycle. Now, read the next instruction. When the next instruction is being read, the previous instruction is being processed. So, CPU comes to know when the instruction is being processed. So, during processing of the instruction, CPU realizes that this instruction, the previous instruction, was not a simple add or multiply or subtract or divide instruction. It's a jump instruction. It's a different kind of instruction. So the instruction, the next instruction is not available in this particular place. It's available somewhere else. So inadvertently, an error is encountered. So instead of reading this instruction here, CPU inadvertently read the next physical instruction. Okay? Then it loses one cycle. An error is committed. So the CPU says that there is an error because the next instruction after processing comes out to the jump instruction. The address is here. So if you jump to this location, not to this location. So that instruction is kept back. So CPU loses that cycle, so this cycle is lost. Because the next instruction is not physically at the next physical location. So this cycle is lost. Then you have to have the next cycle. So it means whenever there is a jump type of instruction, inadvertently one cycle is lost. So if a program has got many jump instructions, hardware architecture is not efficient. But truly speaking, in a program, 10% of the instructions will be jump instructions. You don't, every now and then you don't encounter a loop or a jump. Maybe after the, for example, 20 instructions, you have a jump instruction. So it means hardware architecture works well for majority of the programs. Because jump instructions are hardly 10%. Right? So in jump type of instruction, when the program location changed, the hardware architecture loses one cycle. It means for all of the instructions, the effective execution cycle is one instruction cycle. For jump instruction, it takes 2 instruction cycles for execution. Okay? So now, what we understand here is the following, that here instruction takes 2 cycles for execution. But for most hardware architecture executes in one instruction cycle or one message cycle. That's the same thing. So it means this architecture is superior to the precision in terms of fastness of execution. So if it takes 1 microsecond, this will execute the same instruction in 0.5 times, excepting for job substitution. If this is clear, we can move forward. Okay. Now, coming to the microprocessor and microcontroller, I will just go back a little bit. Now, the microprocessor adopts precision architecture. So, this architecture is actually adopted by the traditional microprocessors, right? And the hardware architecture is adopted by microcontrollers. That's why in this, the reason being, the microcontrollers are often called embedded controllers. They are not meant for intensive computation. Suppose you would like to run a MATLAB program, you don't use a microcontroller, do you? You use a microprocessor. Now your laptop is an example of microprocessor. i5, i7, maybe Apple. So all these things are microprocessors. They are meant for intensive computation. When we talk about microprocessor, they are meant for intensive computation. Microprocessors are meant for intensive computation. It means you do a lot of computation, you do graphic processing, you do programs which will take time to execute. And the microprocessors operate nowadays with gigahertz clock speed, very high clock speed. High clock speed. High clock speed. On the other hand, if you talk about microcontrollers, they are not made for intensive computation. You don't run a MATLAB program in a microcontroller like an Intel 8051 or big microcontroller. What you do here is this: the microcontrollers are meant for simple control applications. Alright? Simple control applications. Involving IO devices. Say for example, we would like to control the temperature of this room exactly at 28 degrees Celsius. We have the AC is running, so the AC has to be turned on and turned off. The temperature of this side is controlled at 28 degrees Celsius. So we have the feedback control. For the feedback control, we need input-output devices. So this requires input-output devices. And sometimes these IO devices are inbuilt here. So microcontrollers have inbuilt IOs or peripherals. Say I would like to use something for my voice recording. The voice is an analog signal, so that has to be stored. So we need an AD converter because the storage is digital. So this needs an AD converter. So AD converter is part of the microcontroller. So this involves, these are the inbuilt IO devices which are peripherals. Now this is inside the microcontroller. You don't have to have interfacing. But a microprocessor, the objective is going to be different. You are not using this for a cell phone. The cell phone has a microcontroller, not a microprocessor. But a laptop has a microprocessor because this needs to do a lot of computation. So here, the memory is outside, memory is external, IO devices are also external. IO devices are external. So in a microprocessor, the memory is, these are the various differences. For intensive computation, operates at high clock speed, right? And the memory is external, and the IO devices are also external in a microprocessor. On the other hand, In microcontrollers, this is meant for simple control application. The I/O devices are inbuilt, and this operates on lower clock speed. Lower clock speed. The microcontrollers are usually at megahertz clock speed, which means 10 to the power 6. Gigahertz is 10 to the power 9. So you know that the clock speed is order of magnitude below here, and that is why you need a better architecture. It means with the lower clock speed, you need the architecture which optimizes the control flow. So you have separate program memory and the data memory, but the clock speed is low and it is inexpensive. A microcontroller is available in a couple of hundred rupees, right? The microprocessor is much more expensive because a lot of VLSI, lot of architecture advancement has gone into it because the object is something different, and this is entirely a digital IC, entirely a digital circuit. But microcontroller is a mixed signal circuit. By mixed signal, we understand combination of analog and digital. So for example, you have to have sometimes an AD converter inbuilt here. AD converter is a mixed signal circuit. It has analog interface, also digital. So this is a mixed signal circuit, and when you say mixed signal, in the same monolithic IC, you cannot optimize everything. You have to optimize some parameters. Here the optimization is basically with respect to the speed, and the architecture is much more advanced to carry out intensive computation. But here you want simple control application, like control of let us say panel of a vehicle. You have speedometer, you have fuel gauge, everything has to be displayed nicely. That would necessitate the use of a microcontroller. So in this room, we have many microcontrollers, but only a few microprocessors. I don't see a laptop here. If there's a laptop has a microprocessor. So number of IC wise, microcontroller is much more than microprocessor, and that is why it's important to read about that. Because if you see that the number of applications, microcontroller application is voluminous. And the manufacturers of microprocessor are only a few. Intel, Motorola, Apple, Zilog, and so on. The microcontrollers have got many manufacturers. Because it's easy to manufacture microcontrollers because they operate at low clock speed, and to fabricate an IC at a low clock speed is not a very big thing. But to manufacture an IC which is operating at a gigahertz clock speed, you have to optimize so many parameters, right? So this is much more expensive. But when you talk about miniaturization, have you seen a Swiss knife? Swiss knife. Okay. The Swiss knife is a knife having so many functionalities. It has a knife, it has a scissor, it has a scalpel, it may have a screwdriver. Everything is single package. Maybe a water opener. So it means a single knife has so many functionalities. A microcontroller can be compared to a Swiss knife. It means you don't have a very big thing. Of course, you cannot cut a wood actually using a Swiss knife, but you can definitely do some small functions, right? You can open a cold drink bottle maybe. Okay, you can maybe cut vegetable and so on. So it means Swiss knife has the multiple functionalities, but having very small capability, and that is analogous to microcontroller. It's a small device, but having multiple functionalities. You may be having a AD converter, you may be having a D-tray converter, you may be having I/O, serial I/Os. So for example, if you want to connect a microcontroller to a PC, how do you connect it? Maybe you have to have a serial communication that is embedded there. So you don't have to have any extra IC there. So it means a single IC, everything is actually in a single chip. So the single chip has got the CPU, has got the program memory, has got the data memory, has got the I/O, everything built in a single chip. So when you talk about microcontroller, we talk about small application which is compact, which is miniaturized. But microprocessor, everything is external. I only say the CPU is optimized, this is microprocessor. But the memory is outside, the IO is also outside. So if you want to build a small system, better you go for a microcontroller. Don't go for a microprocessor. Because the application domain is entirely different. Now, with this background, let us take a simple microcontroller and see how we can program it, how we can write small program with microcontroller. Now, if we can do or understand any microcontroller, you can understand any other microcontroller as well. But the thing is that a microcontroller would require only to understand a single IC, that's all. A single IC is enough for your control application. Okay? So with this background, let us go forward and then let's go for a typical microcontroller. I will remove the physical architecture, although this is extremely important. I will only keep hardware architecture because hardware architecture is widely used for microcontroller. We'll take an IC which is, if you want to have a break, it's alright, but let me know actually. But I'll continue. Okay? Now we have set an IC which is called PEAK. Now PEAK stands for Peripheral Interface Control. How many of you know about PEAK microcontroller? How many of you know about PEAK microcontroller? Have you used it? Have you done programming with it? Anyway, so why I chose PEAK microcontroller? Because it's a typical microcontroller with peripherals and which has got hardware architecture. And it is easy to program. And PEAK stands for Peripheral Interface Now, we will say this is basically manufactured by one company called Microchip. If you visit this website, www.microchip.com, you will see a variety of PEAK microcontrollers, which can be divided into three distinct ranges. One is called a low-end architecture, other is called a mid-range architecture, and the third one is called high-end architecture. The microcontroller started, if you see the history, the microcontroller started along with the development of microprocessors. Starting from 1970s, after the VDSI came into existence. The players are few. Initially, Intel was only manufacturing microcontrollers or microprocessors. Intel. Okay? So Intel started with 4-bit with a few transistors. Then went with 8-bit, then with 16-bit, and so on. So starting from 1970s onwards, there was a gradual development of microprocessor and microcontrollers. But I would say microprocessor to be the feasible development because they affected our daily life. You see that in 90s, 93 Pentium was introduced. How it affected our life directly is because of the PC evolution. The microprocessor evolution was basically PC evolution. Microprocessor was linked with PC evolution. Okay, and this is a visible development. So it was basically very, very visible. Now if you go to the market, when you ask for a cell phone, you don't really ask for, I require a cell phone with an ARM processor. You don't ask for that. You you ask for whether you'd like to go for a Motorola or a Nokia or an iPhone and so on. But if you go to buy a laptop, you very precisely say, no, I need an i5 laptop, I need an i7 laptop. So you basically mention a laptop but never processor. So it means when you talk about a PC, you talk about the processor. But when you talk about a cell phone, you don't talk about any processor. Now that is invisible, but that is also having been developed. So the development of microcontroller is invisible. Microcontroller has also developed, but this development is not very common or very apparent to the common man. I would like to say this is invisible development. It is invisible. It is developed along with the PC architecture, so this is invisible. So microprocessor is a visible development. The microcontroller, although this has got a large impact in our daily life, the development of microcontroller is sometimes invisible to the common man. Okay. Now, this microchip was introduced sometimes in 1980s. Okay. Now, we will be discussing about an IC which is the mid-range architecture. Alright. So this is PIC 16F8778. For simplicity, I have chosen this to be 8-bit. And what extra this has? This has got 35 instructions. You can log it within a couple of days. Please believe me. You can log this instruction, everything within a couple of days. If you are sincere, you can log it in a single day. It is only 35 instructions. On the other hand, 8085, if you compare, it's a microprocessor having principal architecture. These have got 246, something like that instructions. Right? So you see the complexity of a microprocessor. Sometimes this type of instruction is called RISC instruction, reduced instruction set. So this follows architecture called RISC, reduced instruction set computing. And this follows an architecture which is a CISC, complex instruction set. That's why you know there are so many instructions. Why do you need so many instructions? You realize instructions by having simple instructions. Now only 35 instructions are easy to remember. Now 246 for every command you have instruction, that is really complex. And that's why this is called complex instruction set. Now you can do everything that you can do with 85. Okay, we have instructions. But for one instruction, we have to write 2 or more simple instructions. Right? That is concept reduced instructions. Everything can be realized using this. Now, what else has? These are got about 15 interrupts. Okay? Inbuilt timer. Timer is a peripheral. Inbuilt timer. About 2 maybe. Okay? And then what you have is a inbuilt AD converter, analog to digital converter. You have 33 IO pins. It means you can have 32 digital input output. Right? Serial interface. And so on. This is I2C. I2C stands for inter-integrated circuits, which is one of the serial interfaces. Serial peripheral interface, and so on. Use are universal receiver, asynchronous UART, universal asynchronous receiver transmitter, and so on. So the single IC, and also this has got about 8K of program memory. Okay. and about 300 something. To be very precise, it is 368 or so, 300 plus into 8 data. This also has got some electrically erasable programmable memory. So it means a single IC has got so many facilities here. 35 instructions, 15 interrupts, inbuilt timers, 18 converter, having 8 channels. 8 channels. Static IO pins, the serial interfaces, and then 8K of program memory and more than 300 data memory. And also we have some electrically erasable programmable data memory. So we have so many things in a single chip. Okay. So let us see the architecture of this big microcontroller and see how we can write simple program with a big microcontroller. So this is the main architecture. How to break actually? How is it?
T30.
T330. Okay. What's the time now?
16.
350. Okay.
15 minutes.
Architecture of so this is the main CPU. Okay. I am just giving you a simplified version of the processor. Very simplified version. Right? Now CPU is an 8-bit CPU. Right? So this is an 8-bit CPU here. So it can process 8-bit of data. What meaning of 8-bit CPU? The processing capability is 8-bit. You can add 8-bit number, you can subtract, you can multiply. You cannot do anything which is more than 8-bit. The processing capability is only 8-bit. The arithmetic logic unit is 8-bit. So you have two memory banks here. One in the program memory and other is a data memory. So this is the program memory and you have the data memory. And the program memory, this has got address which is coming from the CPU, and the address is 13-bit address. So, can you tell me how many programs can be written here? How many instructions can be written here? Yes, please. In 13-bit of address. How many instructions? And here every instruction is single word. Unlike 885 where you have single byte, 2 byte, 3 byte instruction, all the instruction is on the same side. That is 14 bit. So it means the instruction size here is 14 bit. So each instruction is 14 bit. So this is instruction. So how many instructions can we write here?
2 to the power 13.
2 to the power 13. 2 to the power 13 is equal to 2 to the power 10, 2 to the power 3, that's equal to 8k. And we have this instruction is 14 bit, so we have 8k into 14 is the size of the memory. Right? So this is the program memory. What about the data memory? For simplicity, I will only take 256 bytes of data. So let me say that the address here is 8-bit address. Only 8-bit address. And the data, of course, obviously has to be 8-bit because it's 8-bit processor. The data is 8-bit. So this is your data in this case. Alright, so when you talk about the data memory, it has got 256 bytes of data. So 256 bytes. Now the data and IOs are mixed. Data is sometimes called the file or the register file. Registers. You see that in 885 what you had is A, B, C, D, HL. You don't find any register. The register is a part of the data memory. So you don't have any specific register here. You can refer to the register in the data memory. So registers are part of the data memory. So we can say that a part of the data memory is register. Right? And we sometimes call this data memory as register file because it has got a file of registers. Okay, what is register? Register is also a storage location. So instead of having individual register like A, B, C, D, they are mapped to the data memory. Okay. Now, the data memory is organized in a different way. It will be an interesting way. But first of all, let me discuss about the program memory. The program memory has got 2 to the power 13 locations. So if I say these locations like this is program memory map. So program memory map is like this. So if you want to understand the program memory map, this is our program memory. Very long memory, and usually the program memory is non-volatile. And in this processor 16F877A, you have an alphabet A here. A stands for flash. Flash means it can be erased in a single clock cycle. It is a permanent memory which can be programmed electrically, can be erased also electrically. So this stands for the flash memory. So the program memory is a flash memory. And nowadays the flash memory is pretty common. So all the memories which are not volatile nowadays mostly are flash memory. So in this case we have 8K of flash memory, having each having 14 bit locations, 14 bit capability. The memory map is as follows. So if you represent this memory like this, this is the lowest address, right? So we call this as 0000H. Now 13 bit can be represented as 4 nibbles, right? This is 13 bit. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So this is one nibble, 4 bit. A second nibble, third nibble, and this. And we represent each one as a hexadecimal number. So each one can vary from 0 to S. So this is starting with 0000. So the starting address here is 0000. That is our starting address. A stands for hexadecimal. And the last address is 1 is. So it basically address increments 00001, 00002, 3, 4, 5, 6, and so on. Now, when you place a reset, every IC is having a reset or a power on. When you switch on the power, the program automatically goes to 0000H. The program has to start from this location. That is the way it is designed. So this is called reset vector. When you reset it, program execution starts from this location. This is called the reset vector. And 0004, whenever you have an interrupt will drive the execution to 0004H. The execution has to start from this location. This is called interrupt. Although you have 15 interrupts here, all interrupts will lead to the same vector. You may be asking this question in your mind that how can the 15 interrupt, all interrupt will take the same interrupt vector? It is true. Now when you come to this interrupt, you write an interrupt service routine. In the interrupt service routine, you will find out which interrupt has interrupted the system. It's a timer interrupt, a AD converter, a serial port, which interrupt has caused this interrupt. So that can be found out by writing an intelligent interrupt service routine. All interrupt will lead to or will make the program point to this location 0004H, and in the ISR interrupt service routine you have to find out which interrupt has interrupted. Now you are free to write the program if throughout this memory excepting this location. Now this location is a reset vector. Now when you press the reset, when you switch on your power supply, the program starts from this location. So if you write your program here, say this is my program. Okay? So this is the program which I want to write. User program. Right? If the user program is here, the reset vector at this particular location, please write an instruction jump. In this case is called go to. It is a go to instruction. Write go to maybe a user program. Go to user. The user is the address of the user program. So if you are writing your program here anywhere in the program memory, it means whenever you press a reset, your programs will be executed. So to take care of that, you write at the reset vector an instruction which is go to user. User is the address of your program where you start. Okay? And in this case, if you feel that this is the space is not adequate to write a inter-service routine, you can also write jump instruction here. Go to ISR. And ISR is an inter-service routine. You may write ISR somewhere else. So it means the interrupt vector should contain a go to instruction to actual address of the routine which you are writing. This is the program memory. So you are free to write your program. And how to write the program? You take the help of the program. So you have the IC, it's a 40-pin IC. It's a dual N-pin package. You can buy it maybe about 300 400 rupees. And this has got 40 pins here. 1 to 20 here. Then here 21 to 40. So when you have this IC, this has to be programmed. How do you program it? You use a program. With a programmer, you place this IC and download the program to the program memory. It basically resides in the program memory automatically. If the previous thing is erased, you cannot just program part by part. No, that's not possible because it's a flash memory. If you want to erase it, everything will be erased. You don't say that no, I have stored my program here partly and then I'll write a program here. You have to reprogram the entire 8K of memory. Because fast memory means once you program it, before it has to be completely erased. And erasing is complete. Irrespective of the fact that you are only programming a part of it. Right? So this has to be erased completely, and then the programmer will get the program from your PC. In the PC you have the assembler running, and assembler is freely available here. Now why is it so popular? Assembler, everything is freely downloadable from microchip.com. And assembler for this is a software called MPLab. So MPLab is an assembler. What it does actually, what is the role of an assembler? It converts the assembly language into machine. The assembly language is English-like language. So for example, R. R is not a language which can be understood by a microprocessor. It understands only bits, 1, 0 and so on. So what assembler does, it converts to assembly language. To machine. So the assembler converts the assembly language to machine code, and machine code is a strings of ones and zeros. They are also called binary code, and sometimes they are available in the form of what is called an Intel hex file. Intel has the format. So an Intel hex file. So this is basically a binary file. So it's a binary file which contains the address location and the binary code, and that is checksum to ensure that there is no error during transmission. Right? So the assembler converts the assembly language to the machine code. The machine code can be downloaded to the programmer in which the IC is fixed, and the programmer will program the relevant part of the program, and the chip is programmed. Now, once the IC is programmed, what you do, you take out the ICs, place in your system, give a crystal clock, watch this to the IC. Because to make the IC functional, you need a power supply, you need a clock, that's all. You don't need anything else. So what you need here is that you need a power supply, plus 1 volt, you need a watch crystal connected to the relevant pins of the IC. Of course, it has to be grounded to the capacitors here, and then VCC and ground. This is your VCC and ground here. That's all. And you also have a reset input here. And if you want to reset the system, you apply a low signal. So we will take a simple experiment. Write a simple program to light or to blink the LEDs, light emitting diode, using the IO tools. Okay? Once IC is programmed, what you need is power supply, the crystal, that's all. So this becomes a compact system. And IC is sometimes called a single chip computer. Okay? Peripherals, everything is in there. Now coming to the data memory, this is let's say 256 bytes. So to make the operation more convenient, the data memory is divided into 2 banks. So what we have done here is this: we have divided this into 2 banks, 2 equal banks like this. One is called bank 0, other is bank 1. Right? We have cut this into 2 halves. So for example, this is a big hall. Okay, for a classroom it's alright. But if you have to convert this into a living room, maybe this room is too big for a small family. So what you do, you divide this into 2 parts, 2 equal parts. Microcontroller is a small IC. It is not a very powerful processor. So to handle this big memory, it's sometimes inconvenient. So what is done in this case is that it's a data memory, and data are fewer in numbers. So in this case, what is done, it is divided into 2 halves. One half will contain 128 bytes. 256 by 2 is 128. So this has got 128 bytes. And this also has got 128 bytes. And we refer to as bank 0 and bank 1. You may be wondering still, what is the need? What is the advantage? Why do you divide this into two banks? It's not very clear. Now, if you divide this into 2 banks, the addresses will be different. The addresses in this case will start with it's a 8-bit address. So the number of data will be 2 to the power 8, which is 256. And 8-bit means these are 2 hexadecimal numbers. So this is 4-bit, we have 4 bits. So we represent this by two hexadecimal digits from 00 to SS, right? So this is 00H and then 01H and so on. And when we reach here, it is half of this because this is only 128. So this is 7FH. We have divided this into two halves here. And the next half starts from this. It is 80H, 81H, and then FFH. So if you join this here, this becomes a continuous memory from 00H to FFH. But for our own convenience, we have divided this into two equal parts. From 00H to 7FH and then 80H. Now if you carefully look to the addresses here. Now do you find any difference between this set of address and this set of address? Address of bank 1 and address of bank 0. Do they look similar? Do they look quite similar? Because here also 0, 1, 2 and so on. This is also 80, 81, 82. The difference is in the MSB. As some of you have already said, the MSB is 0 here and MSB is 1 here. The MSB is different. Except in MSB they are same. So that makes a difference. Because if you are actually in bank 0, you have to forget about MSB. So instead of 8-bit address, you are dealing with 7. That's 7. That's a 7. Now, in this case also, if you are in bank 1, instead of 8-bit address, you are handling 7-bit address. Because you know this is MSB equal to 1, you don't have to remember that. So it means instead of 8-bit, you are handling 7-bit. That's a 7. Now, 1-bit saving is saving in cost as well. It means if we are in bank 0, we don't have to bother about 8-bit address. We can handle this with 7-bit address. And we may have extra bit which is called RP0, which will remember the MSB. If RP0 is 0, we are in bank 0. If RP0 is 1, we are in bank 1. And this bit is called the bank selection bit. Now when you write or design a microprocessor or a microcomputer, you design in terms of bits. You design in terms of logic gates. You design by number of flip-flops, number of registers, right? Here every bit setting is important. Now when you say I'm using 7-bit address, you are basically having a significant amount of setting. Now when I say instruction is 14-bit. If you look at the instruction has got two distinct parts. One is called opcode, other is called operator. So this is the instruction. So part is called opcode, other part is called operator. And you only have 14 bit. You only have 14 bit to accommodate opcode. No. So if this is your bit 0, this is bit 1. This has to be bit 2. So this operator, when you say we have a data, how do you specify the data? The data is specified as an address. You can say that okay, I want register A. What do you mean by register A? Register A must have its address. Register A may be somewhere here, but what is the all the address of the register? Address is basically just by 8-bit. So in that case, what we have here is that A can be having an 8-bit address, but in our case, instead of 8-bit, we have reduced this to 7-bit address. And the address has to be specified as a part of the operator. When you say I want to add A and B, or A with a register which is in the CPU, that is called working register. If I want to add A to a register called W here. Now the address of A has to be specified. Now what do you specify the address? It has to be part of the instruction. And the instruction has to contain all information. The code, which means what type of instruction is this? Addition, subtraction, jump, go to, or maybe rotation, so on. And then what is the operand? And the operand has to contain the address of the data. And here we are using 7-bit address. And this address sometimes is called direct. This is called direct address. It means the address is directly available as a part of the instruction, and hence we call it to be direct address. Now, if the address is not available in the if the address is not available in the operand itself, that sometimes is called indirect address. Say something like that, I will say that I can talk to you directly. Okay, I can send email, I can make you a phone call, but suppose I don't want to talk to you directly, I'll take the help of a friend, who is a good friend. I'll say, can you talk to, what's his name? Akash. Can you talk to Akash? I want some information from Akash. Right? So that's the way of indirect addressing. So indirect addressing can be done when you don't address it directly, you address through something else. And that, in this case, is called the file selection. Now that is a way of indirect addressing. It means the indirect addressing can be achieved anywhere in the data memory from 00 to FF. Right? So indirect addressing has the 8-bit address. The direct addressing invariably has 8-bit. And the direct addressing is basically a part of the operand. Alright. So this is about the architecture. Now let us go a little bit inside the architecture, because this doesn't give us a very good picture. Okay? You have the CPU, you have the program memory, you have the data memory. But as a somebody who wants to know a little more about microcontroller, I think this is not enough. Right? We need to go a little more deep into this. Okay? Let us go deep into this. Okay? Now, this is in our mind, but this is not enough. So, okay. Now, this is our program memory.
So I give permission.
Yes.
And we have to rearrange it here only, so that time will not.
Fine. It's all right. That's okay. Whatever is convenient to you.
So after is there.
Okay. So maybe we'll have 5 minutes break now. And
Yes,
then you want the PPT solved here? Absolutely no problem. I have no problem. I will like to
5 minutes complete with it. You can answer the matter.
Okay, fine. All right. So we'll have a break. We'll find after maybe whatever.
Please.
Actually, it was a very sketchy architecture in terms of the block diagram. Now we'll just go deep into the architecture. So what we have here is a program memory. Which is 8K into 14-bit. And this is addressed by a counter called program counter. I write here probe counter, and this is 13-bit counter, and the address here is 13-bit. This is the address in this case, and the address here is 13. Okay, and what we have here is 8-level PC start. It means the program counter values can be stored up to 8 levels. You can store 8 values of the program counter. Now, why it is needed? Basically, memory which can store 8 program counter values. So this is 8 into 13. So this is necessary in case of call instruction, in case of subroutine. Okay, you have to return back to the original program. So to return back to the original program, you have to store the value in the program counter PC file. Okay, and what comes out of this program memory is instruction, and this instruction goes to what is called an instruction register. Instruction register. And what is the size of this register? 14-bit. Because instructions are all 14-bit. All instructions are 14-bit. So each instruction is 14-bit, and that is stored in an instruction register. And then what we have is instruction decoder. We have instruction decoder. Instruction decoder. Now, here is the data memory. So this contains the data. Okay. And what is the size of this? 256 bytes in 2 banks, bank 1 and bank 2. They already said that we divide this in 2 banks for our own convenience. So what we have here is the address multiplexer. Address multiplexer. This takes address from 2 sources. We already said the address can be 7-bit address. Because if you talk about a bank, the bank address, the address of the data in a bank is actually 7-bit. So this address is 7-bit. And this address, we would like to call this address as a direct address. Because we will be giving the address in the part of the instruction. So this is the direct address. Direct. And where will this address come from? This address is a part of the instruction. It is basically will come from this. This is a part of the instruction. The 7 bits of direct address is a part of the instruction. Now what about the other possibility? This is the indirect address, which can be obtained from a register called FSR, file release register. This would be the other source, and this is 8-bit address. And the other 1 bit, if it is a 7-bit address, we need the 8th bit, right? The 8th bit comes from RP0. RP0 is called a bank selection. If it is 0, we are basically in bank 0. If it is 1, we are in bank 1. That's the bank selection. And this combinedly makes 8-bit of address. So we are addressing a 8-bit data memory, which comes from either from a direct address or indirect address, depending upon whether it is a direct address or indirect address. I would like to do the backslash. Now, that is, of course, a very important part of this CPU is called arithmetic logic unit, ALU. Right? So this ALU does all the arithmetic operations like addition, subtraction, multiplication is repeated addition. So this does all arithmetic operations. And the data comes from the data memory through the data bus. This is the internal data bus, which brings the data from the data memory area. This is 8 bit of data, and this data can come from a register called W, and W stands for watching register. This is similar to accumulator in case of 8085. The result of the ALU goes to W. It means if you add two numbers, the output must be W, and the W becomes a default operand for the ALU. So you cannot add anything but W. So this is the architecture that we have. The W is a register which is the output as well as the input of the ALU. Alright? And the other part is coming from the data memory. So the data memory is free here, so you can get the other operand from the data. It means if you want to add something, you have to add that data memory with W. So W is an important thing. And the result of ALU is stored in W. And at the same time, it is also in the register called the status register. The status register stores the status of the operation. It means whether there is an overflow or not, whether the carry generated or not, there is a digit carry or auxiliary carry or not, whether is a negative number or a positive number, all the information will be reflected in the status register. It's a unit list. FSR is also an 8-bit register. This is the indirect access. Indirect access. And this status register is actually from the data memory. Now the data memory, as I already said, is also the register file, because this contains the registers as well. Right? So the registers are part of the data memory. So I can say that the registers are here. Now unlike 8085 where you have A, B, C, D and they don't have any address, here the registers in the data memory, they have also address. So it means you refer to the register as the corresponding 8-bit address. Now you can say what is status here? The status is shown here, but it is a part of the data memory. So it is mapped somewhere here. Similarly, FSR file selection register is here. It's also part of the data memory. And all the registers have their own 8-bit address. Now we have already said that we have two banks. Now let me redraw these banks once again and see what is inside the bank. Now we have two banks in the data memory area, and the banks are bank 0 and bank 1. So this is our entire memory, and we have divided into two different banks. That's what is like this. And this is bank 0 and bank 1. The necessity of this division is obvious because we are only handling 7-bit address, not 8-bit address. So these banks are made from the same memory. So these are the memory locations of this bank. This goes on like this. Starting from 00H to 01H, 02H, 3, 4, 5, 6, 7, 8, and then finally FFH. This is FE. Sorry, this is not FF, this is 7H. 7F, 7E, and 7D, and so on. And here we have 80, 81, 82, 83, 84, and so on. 6, 8, 7, 8, 8, and then so we can be in any one of the banks. Imagine that these banks are actually small rooms. A big room is inconvenient for a single person. For the convenience sake, we have divided a big space into two equal space. Now one can be here or one can be here. Suppose you have a big patch of area, a big hall is available to you, you divide that into equal parts. Now you can be in any one of the rooms. You can either be in drawing room or in the living room. Now, if you are in any one of the rooms, what are the things you would like to have in both the rooms? Yes, please. You can be in any one of the rooms, but you don't have to switch from the room 1 to room 2 every now and then. You would like a common facility in each of the rooms. What is the common facility you must be having in each room? Electricity, okay, fine. What else? Suppose, when would you like to go to some other room? Please. You must be having some necessary thing in each of the rooms. Maybe refrigerator. Okay. Now I would like to say that you must be having a telephone connection in both the rooms. A single line cannot be parallel connection. It means by being in any one of the rooms, you will be able to lift the phone. You have one connection here, the same connection is also available to others. So some of the registers are actually common. It means without switching the room, suppose say for example you get locked inside the house. How will you come out of the house? You don't have any mobile phone. You have to call somebody. So telephone connection is extremely important. So you must be having phone connection in both the rooms. So the input and registers, so the essential things are something like input and registers. The input and registers are available in both the banks, bank 0 and bank 1, because it can be bank 0 or in bank 1. Being in one bank, you should be able to access to input and registers. Input and registers are common. Some of the registers are common. The registers are as follows. I am only giving you a few registers. And what are the registers we have in these banks? The registers are the following. So we have this register which is called indef. Indef here and indef here. They are common. It means this is the important register which is basically for indirect address. Okay? The status register is extremely important. So these have to be both the banks. So status register is address 3 here, status and status. The register which are important should be in both the banks. And these are the important registers. And then FSR. FSR is basically for the indirect addressing. So being in any bank, you should be able to do indirect addressing. So this FSR is here. FSR is also here. It means if you change the register in any bank, the register is also affecting the other bank as well. If you change status in this bank, status in this bank is also affected, like the phone connection. Whatever you do with this phone, similar thing will be happening with the other phone as well. I mean, you can receive or dial from each one of the phones. So these registers are actually common in the sense that you can read or write to this register in any one of the banks. So these are the three registers which are common. Another register which is common is PCL, Program Counter Latch. PCL here. And this register is timer 0. Let me write down a few registers. This is option register. All are 8-bit. This is all 8-bit registers. This is port A. Port B. We have various ports here. Port C. Port D. And port E. We have 5 ports here. And the corresponding registers here are crease A, crease B, crease C, crease D, crease E. I explained about this. So, and the registers continue up to 1FH here, and this is 9FH. So 1FH means this is 32 bytes. So this is 32 bytes. So this is 32 bytes here. So we have 32 bytes here, and this also 32 bytes. So remaining are general purpose area. General purpose RAM area. So if you want to use the general purpose data, they can be written here from 20H to 7FH, and this is 9FH. So this is K0H to FH. Okay, so they are general purpose area. So which means 128 minus 32 is 96 bytes here. This is also 96 bytes. And this is called special purpose register. Special purpose register. So this 32 byte in bank 0 and 32 byte in bank 1 are called special purpose registers. So these are got some special meaning. Of course, I am not writing down all the registers here which you can get to the data set. Go to microchip.com and download the data set. So for microcontroller, you don't have to refer to any book, especially for peak microcontroller. This is easily available. All the details are available in the data set. Download the dataset of this IC 16877A. The details are available in the dataset. Now, this is 32 bytes here and 32 bytes here. These are special purpose registers. This is 64 bytes. The remaining 192 bytes are general purpose. So you can write the variables, all the other data from there in general purpose. This is also general purpose. Now, coming to the status registers, these are the registers which are extremely special register shows the status of the arithmetic operation, addition, subtraction, and so on. It indicates whether there is a carry, that is a 0, there is a negative number, and so on. So let us see what is this status register. The status register, if you see, this under this values are as follows. We call them to be CPU registers. They are registers associated with CPU. And these registers are first of all a W register. These have got no address. It's an independent register. This is also called the working register. See. This doesn't have any address, that is there. Okay? And then we have the status register. This has got two addresses, 03H or 83H. You can address this by any address. This is band 0, this is band 1. Okay? Now what is this register content of the register? So if you see the register contents are as follows. This is 0, 1, 2, 3, 4, 5, 6, 7. This is the carry flag. If the result will generate a carry, that flag will be selected. That's a carry flag. Okay? This is called a digit carry flag. The digit carry is also known as auxiliary carry. When you add two numbers, so for example, you add these two numbers with here is the result 0, 1. Now if you add this is 0 and there is a carry over here, this is 1. So this is called auxiliary carry or digit carry. The carry which is transmitted from the third bit to the fourth bit. That is called a digit carry, which is DC. And ultimately, this is 0, this is 1, this is 0, this is 1, and then the carry out, which is 1. That's the carry. So this carry is CQ. They are the main carry. So if you add these two numbers, you have both EC and C set. Okay? In the status register. This is a 0 flag. If you add two numbers, the result is 0, J will be set. Third and fourth bits are not used. Now this is RP0, which is a back selection bit. This also has got RP1. If the data memory is more than 256 bytes, there could be third bank also. Bank 0, bank 1, and bank 2 also. So in that case, we use RP1. So if you have RP1, you can have 0, 0 for bank 0, 0, 1 for bank 1, 1, 0 for bank 3, and bank 4 is not present in this case. So this is basically for 3 banks. But we will primarily concentrate on RP0. This is always entered as 0. And this is not being used, so we will keep it. So this is the status of the status register. Okay. So if you want to be in bank 0, you set this bit. You clear this bit. What we bank 1 is set. And then we have some other register, FSR. So FSR stands for File Selection Register. File Selection Register. This also has two addresses. The addresses are here. 04 and 84H. So two addresses, 04H and 84H. Okay. So this contains the indirect address of the data domain. Contains the indirect 8-bit address of the data. This is a data point. So we have a register called indef. So indef is here. This has got two addresses. So this is 00H and 80H. Now this is actually a dummy register. It is not a real register. Now the designer of the microcontroller does a lot of intuitive things. There are a lot of things which are under their control. Now here indef is not a real register. But for accessing indef, they actually need indirect address. So if you say indef addition, they will take the content of the data pointed by FSR. So that is used for indirect addressing. That is for basically for indirect addressing. So any reference to indef, if I say move, say for example A indef, it means this is an indirect addressing. The address of the data is available in the memory pointed by FSR. So data pointer is data pointer is FSR. Okay. So that is indef. It is not an actual register, it is dummy register. Then we have the register which actually is the program counter. Now this is PCL. PCL is an important register which is program counter low. Program counter is how many bits? 13 bit. The program counter is 13 bit register. It basically has the address of the program. It is 13 bit register. So 13 bit it is 8 plus 5. So or 5 plus 8, I would say it is 5 plus 8. 13 bit. So 5 is the lower 8 bit. 8 is the lower 8 bit here. And 5 is the higher bit. So this is PCL, program counter lower. And the upper 5 bit is something different. So this PCL is having two addresses 02H and 82H, and this is a lower 8 bit of program counter, lower 8 bit of program counter. We often call this program counter as PC, program counter. Now we have another register called PCLATH. Right? Now this is not so clear, but this has an address which is 0AH or 8AH. Now this can be translated as the program counter higher 5 bit latch. It is not a higher 5 bit. It is a higher 5 bit latch list. So why is this very important? This decides this is the latch value of higher 5 bits of the program. Now, everything has a reason. So we have to understand what is the meaning of PC latch. The PC latch has the significance like this. Now, if you want to change the program counter, how will you change? Suppose you like to change the program counter. You would like to jump to some other location. How do you do that? Can you change program counter in one shot? Yes or no? Is it possible to change the program counter in one shot? Why not? It is the microcontroller is 8-bit microcontroller. So you cannot do any operation which is higher than 8-bit. It is 13-bit register. So this has to be done in 2 steps. But is it possible to do this in 2 steps? Suppose a counter is running. Can you read the counter in 2 steps? Suppose you are counting something like 0, 0, 0, 1, 0, 2, 0, 3. Let me count the decimal values, right? And then 0, 9 and 1, 0, then 1, 1. Now, suppose I read in one shot one digit only. And it's a running counter. I'm just counting from 0, 0 to maybe 99. Now, at one spot, at one instant, I read this. So what is my lower digit here? 9. So I read 9. So this is my 2 digits. So I read 9. Now when I come back and read the next digit, which is the higher digit, the value has changed. Now what I read here? 1. So what is my result? 90. Is it correct? It is not correct because my readings would have been 0, 9. So if I read the counter, which is running counter, I cannot just go on reading digit after digit. It's not correct because there may be possibility that the value may change, and I will end up with a wrong reading. So the correct thing would be you latch this value. You don't read it in one shot, but you can latch it somewhere else. So you can latch this. Alright? To say temporary value or a temporary 16-bit latch inside, which is 0, 9. And you read this latch which is static. Read a static value. Similarly, if you want to change the program counter, you should change it in one shot. Right? So if you change this fast, say for example, I would like to jump to from this location to let's say 25H. How will you modify the program counter? At every instant you can only do 1 digit. Suppose you choose to do the low digit first. So you take this value, you change it to 5. So what you get here? 0, 5. So you are basically changing the value to 0, 5, not to 25. Then next time it has incremented to 0, 6, you change it to 2, 6. So basically this goes to 0, 5, then to 2, 6, which is incorrect. So since we have limitation of 8-bit microcontroller, we cannot do any manipulation which is higher than 8-bit. So to be able to do that, we take the help of something like PCLATH. It means PCLATH is not the higher value of the program counter, but this is the higher slash value of the 5-bit program. So which means whenever you load the lower bit or the lower digit, the higher digit also automatically gets loaded. So this is your PCL, right? And this basically comes from PCLATH. So it means if you want to change the program counter, it is sufficient you change only PCL and rewrite PCLATH appropriately. So which means if you have a 13-bit program counter, this is PCL. The 5 bits here, 1, 2, 3, 4 and 5, they basically come from 1, 2, 3, 4 and 5. This is PC, LA, UH. Any modification to PCL will download this value to the higher 5 bits of the program. So if you want to change the program counter to a particular value, you make sure that you rewrite it before. Okay? Suppose I would like to say do something like 10101. You rewrite it prior after then you change PCL. So when you change the PCL, you are writing this, automatically this value gets loaded. So that is how you can change the program counter in one clock, one instrument. Okay? That is the program counter lifespan.
So in PCLH, how many bits are there?
5 bits.
5 bits.
But 5 bits means this is actually 8 register.
Yes.
Upper 3 bits are not used. There are actually 8 bits, but these 8 bits, these bits are not used. Okay? You are only concerned with the lower 5 bits. The upper 3 bits are not used. And the program counter start, as I already said, this can store up to 8 level. It means if you want to have a subroutine call, once you call the program, what happens? You have to return back to the original program. So in that case, the next address where you are calling, say you are calling here, call some subroutine SUV. Right? The next instruction is here. So the next instruction address is pushed into the stack. It's stored here. So when you finish this subroutine, you return back somewhere here. So this address is retrieved from the stack. And in that subroutine also you can have another call. In that you can have another call. So these calls actually can be 8 nested calls you can have. You can have possibly 8 loop calls. Okay? So that's why you have 8 levels. So this is about the architecture. So we have discussed about working register, the status, the file registers which contain the special purpose register of 64 bytes, and then we have the general 192 bytes of RAM memory, and we have got 5 ports: port A, port B, port C, port D, and port E. And these 5 ports total have 32 input-output pins, and each port is by default a digital port, and each pin can be either an input pin or an output pin, which means you can light an LED to glow an LED to read the output value, either high voltage or low voltage. To read the status of something, you make them an input pin. So this can be an input port or output port. And whether it's an input port or output port, bit-wise, is determined by a buffer register, that is the trace register of the corresponding port. If the bit is the output bit, the corresponding pin here is O, is 0. If that bit is the input bit, the corresponding bit here is I, which means 1. So if you want to make an output port, make the bit increase to be 0. If you want to make an input port, you make that bit the corresponding to register to be equal to 1. Okay. Now let us go to this IC, and this has got 5 ports. So we'll start with this 5 ports, and the ports are as follows. Port structure, and pin configuration. So these are the ports here. have got 5 ports in this case. Port A, port B, port C, port D, and port E. So we have got 5 ports in this case, and this is the alternative function. Alternative uses of IO pins, and then we have number of IO pins. Number of IO pins. So these are the 5 ports we have: port A, port B, port C, port D, and port E. If you have seen 885, what are the various pins you have in 885? You have, the data bus, the address bus, AD0 to AD7, A8 to A16. What else you have? Interrupts, trap, RST 5.5, RST 6.5, RST 7.5, interrupt, INTR, reset, VCC, and ground, and so on. Now, we don't have address and data here. Everything is available in terms of IO ports. Port A, port B, port C, port D, and port E. Now, the IO ports are general purpose ports. Okay? You have a set of pins which can have multiple functions. That looks nice. So, for example, if in 885 it is AD0 to AD7, you can't use those 7 pins for any other purpose. They have to be used for AD0 to AD7. So, they are fixed. But if you can have that for multiple functions, that becomes more attractive. So in microcontroller, the pins have got alternative uses. By default, these pins are digital IO pins. You can use them as a digital input or a digital output at a given time. They can either input or output. But that flexibility you don't have in microprocessor. The pin is either input pin, say RST 5.5. It's input pin or output pin. Input pin. Can it be an output pin? It is fixed to get input. But in P microcontroller, a pin can be either input or output, depending upon the application. Okay? Now the alternative use of port A. Port A has got 6 IO pins. The alternative use of port A pins are A to D converter inputs. A to D converter. It means this can be used for analog inputs. ADC require analog inputs. So you can have maximum 8 channels. So these are the pins for feeding AD converter in the P pattern. Then port B. Port B has got alternative use as external interrupt source. Interrupt inputs. And port B has got 8 IO pins. Okay. Port C, alternative uses are serial IO, serial input output, and timer IO. And this has got 8 pins. Port D, the alternative use is parallel slave port, and this has got 8 pins. Each port can be a digital IO, that's for sure. But in addition to that, this has got alternative uses of the pin. And port E are used for AD converter input, because we have 6 here and this is 3 pins here, this is 9 pins. So you can easily feed 8 channel of AD converter input through port A and port E. This is AD converter inputs. So, what is the total number of pins here? 24, 8, 8 and 8, 24, 6, 33 IO pins. So, this is the total IO pins. So what is the total number of pins of this P microcontroller? 40 pins. So what remains is 7 pins. So out of 7 pins, what you have is the following: 2 pins for VDD, means this is a CMOS IC. CMOS stands for complementary MOS. So this draws very small power because of CMOS technology. Now 2 pins for VDD plus 5 volt, and 2 pins for VSS. You have to be more reliable. So you have 2 pins. If one pin fails, other pin you are having power supply. And furthermore, if you have 2 pins for VDD, the possibility of noise is also reduced. The noise primarily comes through the power supply. So having 2 pins for VDD and 2 pins for VSS, the noise level is reduced. Okay, and 2 pins for clock, for crystal, right? That is a quartz clock. Okay, and 1 pin for reset, right? 1 pin that is called for MCLR. In peak word, peak language, the reset is called master clear, MCLR. So if this is actually low signal, which means if you want to reset the IC, you ground this. If you ground it, the microcontroller is reset, which means the program starts from 0, 0, 0, 0, right? So that makes total 40 pins. Okay. Now let us see the instruction of. I said it's easy to learn, right? And you can learn it in 2 days. Okay. Now it's not very difficult. Now this is in our mind, right? We know there is a program memory, data memory. We have 2 banks. Then we have the ALU, the working register is the important register. The status is a register which shows the status of the arithmetic operations. We can have direct addressing. We can have indirect addressing. We have the program counter, PCL, PCL, PH. Then we have the program counter start, which can store up to 8 tables of program counter for the loop, for the call instructions. So now, if you see the instruction set, the instructions are straightforward instructions, which we can divide into 3 main categories. So the instructions can be divided into possibly the air conditioning has stopped. Okay, that's the reason. Okay, doesn't matter. I think.
Port A register in Mac is 8 register.
Yes.
And that's where is on the table is port A.
Right. So what happens here is this, that you know that six bits are useful. The remaining 2 bits are not useful. Okay. Out of 8 bits, we only take 6 bits. Although this is a 8-bit register here, that's correct. The upper 2 bits are useless. We only take the lower 6 bits. Right? Similarly, this has got 3 bits only. Upper 5 bits are useless. Only lower 3 bits are useful. Okay? Now, peak instruction can be divided into 3 different categories. First, number 1 type of instruction is byte-oriented instruction. Byte-oriented instruction. The instructions which manipulates byte is called byte-oriented instructions, which handles byte by byte. So, for example, it's very simple. And sometimes we write this assembly language in small letters. You can also write in capital letters. CLRF. You know, clear. CLR stands for clear. F means file register. F means the data memory. A stands for the file register. In big macro, the data memory is also called file register. It clears that particular file register, 1 byte to 00. So if you say clear F status, what it does here, clears the status. Please don't use this, but if you use it as also fine, all the values will be clear. Okay? So this handles 1 byte. Then move F. Very interesting instruction. This is a data transfer instruction. Move F. This handles also the data memory. Okay? Because there is a letter F here. Now move F. We can write it like this. When I write F here, this is the operand. Instead of F, you can write any register value or any variable name. Register means you can write port A, port B, port C, and so on. And then you can write F or W. Now this means move F to F or W. If you have something like this, move it could be this or it could be this. So if you say F comma W, the value F is written to the working register W. And if you say F, the value is overwritten. Whatever is the value, it's overwritten. So usually we write F comma W. So it means move F, that particular file register, to either to F, the same register, or to W. This involves 1 byte. Alright? So this is called, these are called byte oriented instructions. This handles 1 byte at a time. Second type of instructions are called bit oriented instructions. Bit oriented instructions. Now these type of instructions you did not have in 8085. 8085 doesn't have any instructions which handles single bit by bit. But here we can manipulate bit also, individual bits. These are called bit oriented instructions. For example, you can have, say, bit clear file. Now when you say clear F, say port A, all the bits of port A are cleared. But if you want to clear only a single bit of port A, not all bits, that is B. B stands for bit. Bit clear file. Now when you start with B, it's a bit oriented instruction. You are basically handling or manipulating one bit. Bit clear file. A is any register, and B is the number of the bth bit starting from 0 to 7. If it is 0, the 0th bit, 1 the 1th bit, and so on, 7. Each register is 8-bit register. So it means clear the bth bit of the F register. Right? Okay. Now, so for example, there is another instruction, say B, T, F. You don't have to remember so much because the logic is given here. I said 35 instructions. B stands for bit oriented instruction. Bit test file, BTF. Bit test file, skip if clear. Now this is a conditional jump instruction. Bit test file, skip if clear. Right? So what we are going to test here? We are basically testing the bth bit of the F register or F in the data memory. So bth bit, B is from 0 to 7. We are testing that bit. If that is clear, you skip the next instruction. Bit test file. If the bth bit of this particular file 0, bit save file, skip if clear. If this is 0, you skip the next instruction. Okay, similarly, bit test file, skip if set. If the bf bit here is set, you skip the next instruction. This is an example of conditional jump, but this basically tests a bit. That's what this is called bit-related instruction. Okay? As you can clear a bit, you can also set a bit. Like bit set file in B. Clearing means making that bit equal to 0. Setting means making that bit equal to 1. Bit set file F, comma B. The bth bit of this can be set. So this handles only one bit. Now this is unique in microcontroller. You don't have any such instruction in any design. Right? Now the third type of instruction is called literal instruction. Literal instructions. The literal instruction means it is something like immediate addressing. Suppose I would like to load 20H to a register called, say, working register. Okay? Say, I can say here, move LW. L stands for literal instruction. Move LW. K. K is a 8-bit number, which is a part of the instruction. You literally load, literally load the value of K to W. That's the meaning of literal instruction. The literal value is loaded. It means it is loaded as it is. So these are the three types of instruction we have in C microcontroller. We have the data sheet. The data sheet can be available from the website. So we have 35 instructions. And some of the instructions, like we can have something like an instruction, say and here and LW. What does it mean? I would like to ask you this question. What is the meaning of and LW? Can you tell me?
Perform the logical AND operation between on the logical